On December 19, 2025, an object officially catalogued as C2025 None, better known as 3I Atlas, will pass within 167 million miles of Earth. That's 270 million kilometers. Nearly twice the distance between our planet and the Sun. Far enough to pose zero physical threat. Close enough for decisive observation. The window is precise. The geometry, unforgiving. Interstellar comet 3I Atlas entered our solar system from beyond. Discovered on July 1, 2025, by the Atlas Survey Telescope in Chile. It arrived at 137,000 miles per hour. Accelerated to 153,000 mph at perihelion on October 29th. Now, as it recedes outbound, December 19th marks the final night of optimal viewing geometry, before distance and solar positioning degrade signal clarity by more than 60%. This matters because several key instruments face constraints. Ground-based arrays juggle competing priorities. Orbital telescopes operate on tight schedules. Deep space tracking systems balance bandwidth between Mars missions, Starship tests, and an object that will never return. After December 19th, 3I Atlas continues its journey into the dark, and we lose our chance to answer questions that have been quietly accumulating since summer. The anomalies are specific, measured, documented. 3I Atlas exhibits a sunward antitail. Jets streaming directly toward the sun, persisting across millions of kilometers, maintaining collimation in defiance of conventional dust dispersal models. Spectroscopic analysis reveals nickel emissions in its coma. Strong, isolated nickel lines, with iron spectral signatures conspicuously absent. In nature, nickel and iron almost always appear together. Here, they do not. The comet's mass exceeds 33 billion tons, with a nucleus diameter estimated between 440 meters and 5.6 kilometers. That makes it orders of magnitude more massive than previous interstellar visitors on Oumuamua and 2I Borisov. And then, there is the acceleration. Non-gravitational? Doubt. Measurable. Persistent. NASA's Hubble Space Telescope, the James Webb Space Telescope, Japan's XRISM mission, and the European Space Agency's XMM Newton Observatory have all turned their instruments toward this object. What they've captured does not fit neatly into existing comet taxonomy. The carbon dioxide to water ratio stands at roughly 8:1, one of the highest ever recorded. X-ray emissions extend nearly 250,000 miles in a diffuse cloud. The object rotates with a 16.16-hour spin period. Its coma glowing green with diatomic carbon after perihelion. Before we go further, hit like, subscribe, and tell me where you're listening from, because this story is still unfolding, and what happens on December 19th may rewrite what we think we know about objects from beyond our solar system. Tonight is not about panic. It's about precision, about what we can still measure before motion, distance, and silence take over. About recognizing that nature is more imaginative than we are, and that sometimes the most important discoveries arrive not when we're looking for them, but when we're paying attention. This is 3I Atlas. This is not science fiction. This is December 2025. Chapter 1. The object that refused to behave. The alert came through routine channels. On July 1, 2025, the Asteroid Terrestrial Impact Last Alert System, Atlas, in Rio Hurtado, Chile, flagged a fast-moving object within the orbit of Jupiter. At 410 million miles from the Sun, the speck of light was catalogued provisionally as 11 Pal-3s before formal designation protocols kicked in. Within hours, orbital mechanics teams began calculating its trajectory, running simulations to determine whether this was another near-Earth asteroid, a long-period comet returning from the Oort cloud, or something else entirely. The initial velocity profile suggested something else. At 137,000 miles per hour, 221,000 kilometers per hour, the object was moving too fast to be gravitationally bound to our Sun. Its hyperbolic trajectory placed it on an escape path, entering from interstellar space and destined to leave the same way. This marked it immediately as the third confirmed interstellar object ever detected passing through our solar system, following anomalies Oumuamua in 2017, and Totoi Borisov in 2019. But, as astrometric observations accumulated over the following days, something peculiar emerged in the residuals. Orbital solutions account for gravitational forces, the sun's pull, planetary perturbations, relativistic corrections. When you subtract those known influences, what remains should be noise, observational uncertainty, atmospheric distortion, instrument jitter. For 3I Atlas, the residuals were not noise. They were structured, persistent, statistically significant. The object was accelerating in ways that pure gravity could not explain. Non-gravitational acceleration is common in comets. As icy surfaces heat under sunlight, volatiles sublimate, venting gas that acts like tiny rocket thrusters. The phenomenon is well understood, routinely modeled, and typically predictable. But 3 Atlas was still distant, far from the inner solar system where solar heating dominates comet behavior. At 440 astronomical units from the Sun, beyond the orbit of Mars, significant outgassing should not yet have begun. Yet the data showed acceleration. Small, yes, on the order of fractions of a millimeter per second squared, but measurable across multiple observation nights and confirmed by independent tracking stations. Davide Farnochia at NASA's Jet Propulsion Laboratory began updating the object's ephemeris on JPL horizons, incorporating non-gravitational parameters into the trajectory model. The adjustments were subtle but necessary. Without them, predictions for the object's future position would drift, compounding errors as weeks passed. By mid-July, the astronomical community had confirmed 3E Atlas was active. That meant an icy nucleus, a brightening coma of gas and dust, and behavior consistent with cometary processes. This was not a dark, inert rock like Oumuamua. It was shedding material, brightening as it approached perihelion, exhibiting the classic signs of a comet responding to solar radiation. Except the specifics didn't quite match. Spectroscopic observations from the Nordic Optical Telescope and the Southern African Large Telescope revealed a reflectance spectrum with slight reddening in the optical range between 400 and 700 nanometers. The spectral slope measured 22.8% per micrometer, consistent with organic-rich materials found in comets originating from the outer solar system. So far, so familiar. But when researchers analyzed the composition of gases in the coma, anomalies appeared immediately. The James Webb Space Telescope observed 3E Atlas on August 6, 2025, using its near-infrared spectrograph. The instrument captured absorption features indicating an unusually high carbon dioxide coefficient ratio approximately 8. In typical solar system comets, water ice dominates, with Kunghu present but secondary. Here, carbon dioxide was the primary volatile, outgassing at a rate of roughly 70 kilograms per second. This ratio, 8:1, ranks among the highest ever observed in any comet, interstellar or otherwise. What does that mean? It suggests 3I Atlas formed in an environment fundamentally different from the icy reservoirs of our own solar system. Perhaps near a Ku ice line and a protoplanetary disk around a star with different luminosity. Perhaps in a region exposed to intense radiation that selectively stripped lighter volatiles. Or perhaps in conditions we have not yet imagined, because we have never sampled material from that particular stellar neighborhood. One thing was clear by late July. This was not a carbon copy of known comets. The discovery team, led by astronomers using ATLAS and confirmed by follow-up observations from facilities worldwide, submitted their findings to the Minor Planet Center. Designation followed quickly. C2025, non-ATLAS. The C prefix indicated a non-periodic comet, one not expected to return. The I designation came shortly after, marking it formally as Interstellar. 3I Atlas, the third interstellar object on record. Media coverage remained measured. Interstellar objects were no longer complete novelties after Oumuamua and Borisov. The scientific community approached 3I Atlas with cautious excitement. Here was a chance to study material from another star system, to compare its chemistry with our own solar system's comets, to refine models of planet formation and volatile distribution in distant protoplanetary disks. But beneath the surface of press releases and observatory time allocation meetings, a quieter conversation had begun. Because the residuals in the orbital solution, the structured, persistent, non-gravitational acceleration, did not cleanly match standard outgassing models. Simulations attempting to reproduce the observed forces required assumptions about surface area, albedo, volatile composition, and thermal properties that strained plausibility when cross-checked against brightness measurements and mass estimates. By the end of July, some researchers were circulating internal memos questioning whether current comet models were sufficient. Not because 3I Atlas violated physics, it didn't, but because explaining its behavior required invoking conditions at the edge of what existing theory comfortably accommodated. And the object was still months away from perihelion. The real show, the close solar passage where comets typically reveal their nature most dramatically, had not yet begun. So teams prepared. Hubble scheduled observation windows. Swift's ultraviolet optical telescope began tracking. Ground-based spectroscopy campaigns coordinated across hemispheres to maintain continuous coverage as Earth's rotation brought different telescopes into darkness. Everyone knew December 19th was the endgame, the date of closest approach to Earth, when observing geometry would be optimal, when high-resolution imaging and spectroscopy could extract maximum information before the object receded beyond the reach, all but the most powerful instruments. What no one yet understood was how many questions would accumulate between July and December. How many measurements would defy easy categorization? How many anomalies would stack on top of one another until the compounded odds of coincidence dwindled to statistical irrelevance? In July, 3 Atlas was an interstellar comet with unusual chemistry and unexplained acceleration. By December, it would be something else entirely, an object that forced scientists to confront the limits of their assumptions and the uncomfortable possibility that natural comet might not be a complete explanation. This is not science fiction. This is July 2025. Chapter 2. Instruments Watching the Dark. The Hubble Space Telescope turned its wide-field camera, 3 toward 3 Atlas, on July 21, 2025, when the comet was 277 million miles from Earth. At that distance, even Hubble's resolving power could not discern surface features. What it captured was a bright point source surrounded by a diffuse coma, the cloud of gas and dust enveloping the nucleus. But that was enough. By measuring the coma's brightness distribution and applying models of dust scattering, astronomers could place constraints on the nucleus size. The analysis revealed a diameter no smaller than 440 meters and no larger than 5.6 kilometers. The uncertainty spanned more than an order of magnitude, but even the lower bound made 3 Atlas substantially larger than Oumuamua, whose dimensions were estimated at roughly 400 by 40 meters. Hubble's ultraviolet and visible light observations also revealed something unexpected: faint jets extending from the nucleus. These were not broad, diffuse emissions but collimated streams. Narrow, directional flows of material that persisted across spatial scales, far exceeding what dust grains should maintain under solar radiation pressure alone. Collimated jets are common in active comets. They form when sublimating ice vents through discrete surface features, cracks, pits, or compositionally distinct patches warmed by sunlight. The gas carries dust with it, and the directionality reflects the geometry of the active region relative to the Sun. But in 3E Atlas, the jet orientations did not align with expectations. Some were directed sunward, not radially outward from solar heating but toward the Sun. This phenomenon, known as an antitail, can occur under specific geometric conditions when dust grains lag behind the comet's motion and align along the orbital plane. From Earth's perspective, this creates the illusion of a tail pointing sunward. Except in this case, the geometry did not support an optical illusion. Researchers modeling the viewing angles confirmed that the sunward jets observed in July could not be explained by perspective effects alone. Something was actively expelling material toward the Sun, maintaining directionality across distances where radiation pressure and solar wind should have dispersed the particles into a broad, diffuse cloud. Internal memos began circulating among Hubble's observation teams. The language was careful, hedged with conditionals, but the implication was clear. Standard cometary outgassing models were insufficient. Either 3, Atlas possessed surface properties unlike any known comet, or the forces shaping its coma were not purely thermal. Meanwhile, ground-based facilities mobilized. The Very Large Array, VLA, in New Mexico allocated radio observation time to search for molecular emission lines. The Atacama Large Millimeter Submillimeter Array, ALMA, in Chile prepared to probe the comet's chemical composition at wavelengths sensitive to carbon monoxide, hydrogen cyanide, and other volatiles. The Pan-STARRS survey telescopes in Hawaii added 3E Atlas to their nightly imaging schedules, tracking its brightness evolution as it approached the inner solar system. But resource allocation was not automatic. Telescope time is a finite, highly competitive commodity. Every hour spent observing 3I Atlas was an hour not spent on galaxies, exoplanets, supernovae, or any of the thousands of other projects competing for attention. And 3I Atlas was not the only priority that summer. SpaceX was conducting Starship test flights, each one requiring coordination with deep space communication networks to relay telemetry and validate systems for future missions to Mars. NASA's Perseverance rover continued its investigation of Jezero Crater, with data downlink saturating bandwidth during key transmission windows. The James Webb Space Telescope had its own packed schedule, balancing high redshift galaxy surveys, exoplanet atmospheric characterization, and solar system targets. In late July, a scheduling conflict arose. A request for extended Webb observations of 3 Atlas in mid-infrared wavelengths was delayed by 3 weeks to accommodate a pre-scheduled galaxy cluster observation that had been in the pipeline for months. The delay was procedural, not controversial. Priority rankings favored the galaxy work, which had been peer-reviewed and approved long before 3 Atlas was discovered. But those 3 weeks mattered. By the time Webb's near-infrared spectrograph finally observed 3E Atlas on August 6, the comet had moved closer to the Sun, and its activity had intensified. The carbon dioxide mass loss rate had increased, complicating attempts to establish baseline outgassing behavior. Researchers now had a snapshot of heightened activity, but lacked the earlier baseline data needed to model the object's evolution accurately. In scientific terms, this was frustrating but manageable. Data gaps happen. Models adapt. But it highlighted a structural tension in how astronomy responds to transient, unpredictable events. Comets don't wait for committee approvals. Orbital mechanics proceed indifferent to scheduling logistics. The geometry that makes December 19th critical is not negotiable. It is dictated by the laws of motion, the Sun's position, Earth's orbit, and 3 Atlas's trajectory. Missing an observation window because of a scheduling conflict doesn't pause the comet. It simply means the data is gone. By late July, this reality was settling in among observation teams. There was also the radar question. Planetary radar systems, specifically the Goldstone Deep Space Communications Complex in California and the Arecibo Observatory in Puerto Rico, had historically provided some of the highest resolution data on near-Earth asteroids and comets. Radar imaging could resolve surface features, measure rotation rates, and detect structural details invisible to optical telescopes. But Arecibo's 305-meter dish had collapsed in December 2020, leaving Goldstone as the sole operational planetary radar facility in the Western Hemisphere. And Goldstone was booked solid. A formal request to retask Goldstone for 3 Atlas observations in August was denied due to prior commitments supporting Mars missions and near-Earth asteroid tracking under NASA's Planetary Defense Program. The denial was justified. Planetary defense takes precedence, but it meant that radar data, which could have resolved ambiguities about the nucleus size and shape, would not be available. Budget constraints compounded the problem. While Hubble and Webb operated on multi-year funding cycles with some flexibility for directors' discretionary time, ground-based facilities often relied on semester-by-semester allocations. Proposals had to be submitted months in advance, peer-reviewed, and ranked competitively. There was no fast-track mechanism for responding to an interstellar object discovered in July, with peak observation windows in October and December. So the global astronomical community improvised. Amateur astronomers with backyard telescopes contributed light curves, tracking 3 Atlas's brightness changes night after night. These observations, while lower in resolution than professional instruments, provided continuous monitoring that no single observatory could maintain. The data fed into models predicting peak activity, helping professionals decide when to trigger their limited observation windows. University observatories joined the campaign. The Nordic Optical Telescope in Spain's Canary Islands conducted spectroscopy, capturing emission lines from ionized carbon, cyanide, and other molecular species. The Southern African Large Telescope contributed high-resolution spectra, revealing the anomalous nickel emissions that would later become a focal point of controversy. By the end of July, a patchwork observation network was in place, imperfect, constrained by budget and bandwidth, but functional. What emerged from those early observations was a comet that did not fit neatly into existing categories. It was active, yes. It brightened as predicted. It exhibited a coma and jets consistent with volatile sublimation. But the details were wrong. The CO-to ratio was too high. The sunward jets persisted too long. The non-gravitational acceleration required outgassing rates that seemed incompatible with the object's observed brightness and estimated size. And beneath all of this was a quieter discomfort. The realization that humanity's capacity to study this object was limited not by physics, but by logistics. There were enough telescopes, enough expertise, enough interest. What was lacking was the institutional agility to redirect resources quickly, to prioritize an unpredictable visitor over pre-planned projects, to acknowledge that some opportunities, like the passage of an interstellar comet, do not repeat. In late July, a senior astronomer at the European Southern Observatory sent an email to colleagues that would later be quoted in retrospective analyses. The email read, in part, "We have the tools to answer these questions. We may not have the time." Because the object kept moving. And while humans debated scheduling conflicts, 3 Atlas continued its journey toward perihelion, carrying answers that would remain inaccessible if the right instruments were not pointed in the right direction at the right time. This is not science fiction. This is July 2025. Chapter 3. The Tail That Bent Backward. By mid-August, 3 Atlas had moved inside the orbit of Mars, approaching 2.5 astronomical units from the Sun. Solar radiation intensified. Surface temperatures rose. The rate of volatile sublimation increased, and with it, the comet's brightness. And the tail bent wrong. Comet tails follow predictable patterns. The dust tail, composed of micrometer-sized particles, curves gently along the comet's orbital path, lagging behind due to radiation pressure that pushes particles outward but cannot overcome orbital momentum. The ion tail, formed by ionized gas molecules, streams directly away from the Sun, shaped by the solar wind's magnetic field. These structures are textbook phenomena, observed in every well-studied comet for centuries. 3I Atlas exhibited both types of tails. And a third. Imaging campaigns conducted by observatories in Hawaii, Chile, and South Africa captured the dust and ion tails precisely where models predicted. But persisting alongside them was the anomalous anti-tail, a bright, collimated jet aimed directly at the Sun. At first, researchers assumed perspective. Anti-tails are not unprecedented. When Earth's viewing angle aligns with a comet's orbital plane, the dust tail can appear to point sunward, even though it is actually curving away in three-dimensional space. This is a geometric illusion, well understood and easily modeled. So teams calculated the viewing geometry for 3I Atlas in mid-August. The result: no illusion. Earth's perspective did not align with the orbital plane in a way that could produce the observed anti-tail as an artifact. The sunward jet was real. Material was being actively expelled toward the Sun, not merely appearing to point that way due to our vantage point. This demanded an explanation. Plasma physicists proposed that asymmetric outgassing on the nucleus could create localized jets with arbitrary directionality, including sunward. If a volatile-rich region on the day side of the nucleus faced the Sun at an angle, gas and dust could vent in that direction. Thermal models were constructed, assuming irregular surface topography, cliffs, craters, ridges, that could focus sublimation into narrow jets. The simulations produced jets. They even produced sunward jets under certain configurations. But maintaining collimation across the distances observed, hundreds of thousands of kilometers, required outgassing rates inconsistent with the comet's observed brightness. Brightness scales with surface area and activity. A comet with the luminosity of 3I Atlas should not have enough surface area actively sublimating to sustain the mass flux needed for persistent sunward jets. The numbers didn't balance. One model attempted to resolve this by invoking subsurface reservoirs of highly volatile ices, frozen carbon monoxide or nitrogen, that could explosively vent through surface cracks, producing bursts of high-speed gas capable of maintaining directionality over long distances. This mechanism exists in some solar system comets, creating transient outbursts. But 3I Atlas's anti-tail was not transient. It persisted across multiple observation nights, maintaining structure and orientation, while the comet rotated with a 16.16-hour spin period. For subsurface outbursts to produce this effect, they would need to occur repeatedly, in precisely the same location, at intervals synchronized with the rotation, a level of coincidence that strained credulity. Another approach focused on the dust properties. Perhaps the particles in the anti-tail were not typical silicate grains, but larger, irregular fragments that responded differently to radiation pressure. Large particles are less affected by solar photons, and can maintain trajectories closer to their initial ejection vectors. If the sunward jet consisted of centimeter or meter-sized chunks, their motion might remain collimated longer. This hypothesis was testable. Infrared observations could constrain particle sizes based on thermal emission. The James Webb Space Telescope's mid-infrared instrument, MIRI, was scheduled to observe 3I Atlas in September, and the team planned to search for thermal signatures consistent with large dust grains. But as August wore on, a more unsettling possibility was discussed in private conversations and unpublished notes. What if the sunward jet was not passive dust entrained in outgassing, but something actively propelled? This speculation did not appear in peer-reviewed papers. It was too speculative, too far outside conventional computary science. But it circulated nonetheless, in emails between colleagues, in conference hallway discussions, in the careful phrasing of internal research memos. The mechanism for active propulsion was vague. Researchers invoked phrases like internal energy release and non-thermal processes without committing to specifics. The idea was simply that if sublimation alone could not explain the observed jets, then perhaps some additional energy source was involved. Chemical reactions within the nucleus, exothermic phase transitions, or processes not yet catalogued in cometary literature. No one used the word propulsion in the sense of deliberate, controlled thrust. That would have required evidence of technology, and there was no such evidence. What existed was a gap between observation and theory, a region where models failed to converge, where parameters had to be stretched to accommodate data, where coincidence stacked on coincidence until the narrative of just a comet behaving unexpectedly began to feel incomplete. By late August, spectroscopic observations added another layer. The Southern African Large Telescope's high-resolution spectrograph detected emission lines from nickel atoms in 3I Atlas's coma. Nickel is not unusual in comets. It is a trace metal present in primitive solar system materials. What was unusual was the strength of the nickel emission and the conspicuous absence of iron lines. Nickel and iron are cosmically linked. They form together in supernova nucleosynthesis, condense together in protoplanetary disks, and alloy together in metallic cores of differentiated bodies. Their abundance ratio in the solar system is well established, roughly 1 part nickel to 16 parts iron. They are almost never found in isolation. In 3I Atlas, iron lines were below detection limits, while nickel blazed brightly. This was not merely unusual, it was anomalous. Researchers double-checked calibrations, reanalyzed spectra, and searched for instrumental artifacts that could explain the discrepancy. None were found. The nickel-to-iron ratio in 3I Atlas's coma was orders of magnitude higher than any known comet. One explanation invoked selective volatilization. Perhaps nickel compounds had a lower sublimation temperature than iron compounds, causing nickel to outgas preferentially at 3 Atlas's current distance from the Sun. As the comet moved closer and temperatures rose, iron might appear. Another explanation was isotopic, or chemical fractionation, in the interstellar medium. If 3I Atlas formed in a region with unusual metallicity or radiation environment, its nickel-to-iron ratio might reflect exotic formation conditions. A third explanation, mentioned only in passing, was contamination. If the surface of 3 Atlas had been altered by processes unrelated to primordial formation, impacts, industrial deposition, or surface treatments, then the observed composition might not represent the bulk nucleus. That last explanation was not developed further. There was no evidence for contamination, and speculating without evidence is a path to reputational damage in professional astronomy. So the nickel anomaly joined the growing list of observations that did not fit cleanly. By the end of August, the list included non-gravitational acceleration, inconsistent with standard outgassing models, a carbon dioxide to water ratio of 8:1, among the highest ever recorded, sunward anti-tail jets maintaining collimation across hundreds of thousands of kilometers, nickel emissions without corresponding iron signatures. Each anomaly, considered in isolation, had potential explanations. Unusual chemistry, irregular surface topography, exotic ice compositions, viewing geometry quirks. But the anomalies were not isolated. They appeared in the same object, simultaneously, compounding into a profile that did not match any known comet class. Avi Loeb, a theoretical astrophysicist at Harvard and director of the Galileo Project, began publishing essays on Medium exploring the implications. His writing was provocative. He raised the possibility that 3A Atlas might not be entirely natural, that some of its features could be consistent with a technological artifact. The response from the broader astronomical community was swift and critical. Mainstream comet researchers argued that Loeb was premature, that gaps in understanding did not justify invoking extraordinary explanations, that the history of astronomy was littered with anomalies that turned out to be mundane phenomena once better data arrived. This tension between openness to radical hypotheses and adherence to conservative interpretation would define the next 4 months of observation and debate. But in August, the conversation was still muted. The object was still approaching perihelion. More data was coming. And until perihelion passed, until the comet's behavior under peak solar heating was observed, no conclusions were final. So instruments kept watching. Ground-based telescopes tracked the brightening coma. Space-based observatories prepared for infrared and ultraviolet spectroscopy. Plans were made for October and November observations, when 3E Atlas would round the Sun and emerge on the other side, either validated as an unusual but natural comet, or revealed as something that demanded rethinking foundational assumptions. The tale that bent backward was only the beginning. This is not science fiction. This is August 2025. Chapter 4, September 12, 2025. Starship, Silence, and Scheduling Conflicts. On September 12, 2025, SpaceX conducted its 6th integrated flight test of Starship from Starbase in Texas. The launch window opened at dawn, and for the next 4 hours, NASA's Deep Space Network, the array of massive radio antennas in California, Spain, and Australia, prioritized telemetry relay for the test flight. This was not controversial. Starship represented a critical component of NASA's Artemis program and future Mars exploration architecture. Flight tests validated heat shield performance, propellant transfer systems, and orbital refueling concepts essential for deep space missions. The data was time-sensitive, non-repeatable, and directly tied to congressional funding milestones. But for those 4 hours, bandwidth allocated to 3A Atlas observations was reduced to 0. The conflict was procedural, not political. Deep Space Network resources operate on a priority hierarchy. Crewed missions first, then flagship robotic missions, then lower-tier science objectives. Starship, as a human-rated vehicle under active testing, occupied the top tier. 3I Atlas, An observational target with no immediate threat or unique once-per-century geometry, at least not yet, ranked lower. The gap would have been inconsequential except for timing. September 12th coincided with a rare alignment when 3i Atlas, Mars, and Earth formed a near-straight line, allowing simultaneous observation by both Earth-based telescopes and NASA's MAVEN spacecraft in Mars orbit. The opportunity to triangulate the comet's position and measure parallax-based distance with exceptional precision occurred once during the entire approach phase, and it occurred during the 4-hour Starship telemetry window. By the time the DSN returned to nominal science operations, the alignment had shifted. The triangulation opportunity was gone. Researchers adapted, using less precise ground-based measurements, but the lost data represented a tangible cost. A small but permanent gap in the observational record. This pattern repeated throughout September. On September 18th, a software update for the Mars Reconnaissance Orbiter required a communication blackout, while controllers verified system stability. The update was mandatory, long-scheduled, and essential for continued mission operations. It consumed 6 hours of DSN time. On September 22nd, an emergency retasking prioritized bandwidth for NASA's Perseverance rover, which had identified a rock sample exhibiting potential biosignature indicators in Jezero crater. The sample required immediate spectroscopic follow-up and high-resolution imaging to guide drilling operations. The data uplink took precedence over routine astronomical observations, including 3i Atlas tracking. On September 27th, JAXA's Martian Moons Exploration (MX) mission, en route to Phobos, experienced a telemetry anomaly requiring extended contact with ground stations to diagnose. The anomaly was resolved, but the diagnostic session consumed bandwidth originally allocated for a coordinated observation campaign involving the Very Large Array and ALMA. Each event was justified. Each decision was defensible. Taken individually, none constituted a failure of process. But cumulatively, they illustrated a structural reality. The infrastructure of space exploration operates at capacity, and observing a transient interstellar object competes with dozens of other priorities, each with stakeholders, budgets, and mission-critical timelines. Dr. Emily Whitaker, a planetary scientist at the Jet Propulsion Laboratory, summarized the challenge in an internal email later cited in post-Flyby reviews. "We have the instruments. We have the expertise. What we don't have is the institutional flexibility to say, this matters more than everything else for the next 90 days. And by the time we recognize that it should have mattered more, the object is already receding." The tension was not between science and engineering, it was between competing scientific objectives. Consider the James Webb Space Telescope. Since its launch in December 2021, Webb's observation schedule had been booked years in advance. Peer-reviewed proposals competed for time, ranked by scientific merit through rigorous review processes. The telescope's capacity was finite, roughly 6,000 hours per year of prime observation time, divided among hundreds of approved programs. In August, a special director's discretionary time allocation granted Webb additional hours for 3i Atlas observations. The infrared spectroscopy conducted on August 6th had revealed the anomalous con-to-ocho ratio and confirmed carbon dioxide as the dominant volatile. Those observations were scientifically transformative, providing data impossible to obtain from ground-based telescopes. But follow-up observations requested for late September were denied. The denial was procedural. Webb's schedule was locked until the next cycle, and reprioritizing existing programs would have disrupted observations of high redshift galaxies, exoplanet atmospheres, and stellar nurseries, each representing years of preparation by research teams worldwide. The denial letter, sent to the principal investigator of the 3i Atlas observation proposal, included language expressing regret and encouragement to resubmit for the next cycle. But the next cycle opened in January 2026. By then, 3i Atlas would be beyond Jupiter, faint and receding, no longer a viable target for detailed spectroscopy. The window would close. The opportunity would not return. This reality created frustration among those advocating for expanded 3i Atlas observations. If the object was genuinely anomalous, if its properties challenged existing models and hinted at processes or compositions unknown in solar system comets, then shouldn't that warrant exceptional priority? Shouldn't the discovery of the third interstellar object, exhibiting behaviors unlike the first two, justify temporarily reprioritizing scheduled observations? The counter-argument was equally compelling. Astronomy is not driven by novelty alone. High-redshift galaxy surveys inform cosmological models. Exoplanet atmospheric studies constrain habitability. Stellar formation research tests theories of star and planet genesis. These programs were not less important because 3I Atlas happened to arrive in 2025. They were planned, funded, peer-reviewed, and essential to advancing knowledge across multiple domains. Moreover, reprioritizing based on anomaly was dangerous precedent. Every unusual observation initially appears anomalous until sufficient data resolves it. Galaxies without dark matter. Pulsars flickering in patterns suggesting beacons. Fast radio bursts with integer-second periodicity. Each triggered excitement, speculation, and calls for immediate follow-up. Each eventually yielded to natural explanations once better data arrived. Jumping to conclusions, or worse, reallocating resources prematurely, risked wasting telescope time on false alarms, while delaying research that would have produced lasting scientific value. So the system proceeded as designed, cautiously, methodically, governed by peer review and priority rankings that balanced novelty against reliability. And 3I Atlas continued moving. By late September, it had crossed inside 2 astronomical units, entering the region where solar heating intensifies dramatically. Outgassing rates surged. The coma brightened from magnitude 12 to magnitude 10, making the comet visible through amateur telescopes for the first time. Citizen astronomers around the world began posting images online, comparing brightness estimates, tracking the dust tail's evolution night by night. Their contributions were invaluable. While professional observatories could provide high-resolution spectroscopy and precise astrometry, they could not provide continuous monitoring. Clouds, daylight, and scheduled maintenance created gaps. Amateur astronomers filled those gaps, creating unbroken light curves that documented every brightening event, every outburst, every fluctuation in activity level. These observations revealed that 3 Atlas was not smoothly brightening as perihelion approached. It was variable. Some nights it flared, increasing in brightness by half a magnitude over hours. Other nights it dimmed slightly, then recovered. The variability suggested discrete active regions on the rotating nucleus, areas of concentrated volatile ices that vented strongly when illuminated, then fell dormant as rotation carried them into shadow. This was normal comet behavior. Except the timing was irregular. Rotation period established by light curve analysis, 16.16 hours. If active regions were fixed on the surface, brightness variations should repeat with that periodicity. They did, mostly. But small deviations appeared, irregularities that suggested either multiple active regions at different latitudes or changes in activity level over timescales shorter than the rotation period. Models attempted to reconcile the data by invoking complex surface topography, cliffs that shadowed certain regions, craters that focused sunlight into concentrated heating, or composition heterogeneities that altered sublimation rates as different terrain rotated into view. The models worked. Barely. They required finely tuned parameters, specific cliff heights, specific albedo variations, specific ice distributions that had no independent confirmation. The models explained the data by adding enough adjustable parameters to fit any data. They were not predictive. They were descriptive. This is a red flag in scientific modeling. A good model makes predictions that can be tested. A model that requires constant adjustment to match observations may be mathematically correct, but physically empty, a curve fit masquerading as understanding. By the end of September, some researchers were quietly acknowledging that their models of 3 Atlas were curve fits, not physics-based predictions. The acknowledgement was rarely explicit in published papers, but it appeared in discussions, in email exchanges, in the careful hedging language used when describing uncertainties. Our model is consistent with the data does not mean our model explains the data. It means we cannot rule out our model. Those are different statements. And as September ended, with perihelion less than a month away, the distinction mattered because the data kept accumulating and the models kept needing adjustment. Meanwhile, the scheduling conflicts continued. On September 29th, the Hubble Space Telescope experienced a brief gyroscope anomaly, a glitch in one of the stabilizing systems that keep the telescope pointed accurately. The anomaly resolved within hours, but protocol required a 48-hour stand-down to verify system integrity before resuming science operations. Observations of 3A Atlas, scheduled for September 30th, were postponed. By the time Hubble resumed operations, 3I Atlas had moved into solar conjunction, the period when it would pass nearly behind the Sun as seen from Earth, making observations impossible due to solar glare and the risk of pointing sensitive instruments too close to the Sun. Conjunction would last from October 15th to October 31st. For more than 2 weeks, 3 Atlas would be unobservable from Earth. It would round the Sun, reach perihelion on October 29th, undergo maximum solar heating, and potentially exhibit its most dramatic activity, all while hidden behind the Sun's overwhelming brightness. When it emerged in early November, it would be outbound, receding, and observational geometry would never again be as favorable. The data gap was unavoidable. Orbital mechanics dictated it. But the timing meant that the period of peak comet activity, the very moment when sublimation would be most intense, when jets would be most active, when the nucleus might fragment or reveal surface structures, would go unobserved by ground-based telescopes and most space-based observatories. Some spacecraft would glimpse it. NASA's Parker Solar Probe, designed to study the Sun's corona, would pass within range of 3 Atlas during perihelion and might capture indirect data on how the comet's coma interacted with the solar wind. ESA's Solar Orbiter, similarly focused on solar observations, could detect disturbances in the heliospheric environment caused by the comet's passage. But direct imaging? Spectroscopy? High-resolution morphology? Those would resume only after emergence in November. Dr. Whitaker's words echoed in researchers' minds. By the time we recognize that it should have mattered more, the object is already receding. And so September ended with a mix of anticipation and frustration. Anticipation for what perihelion might reveal. Frustration at the system's inability to fully mobilize around a once-in-a-generation event until after crucial windows had already closed. The object kept moving. The institutions kept operating within their designed constraints, and the distance between what could have been observed and what actually was observed grew wider with every passing day. This is not science fiction. This is September 2025. Chapter 5, October 8, 2025. Carbon that shouldn't glow. Before 3 Atlas disappeared behind the Sun, one final set of observations captured something that would haunt researchers for weeks. On October 8, 2025, the Gemini North Telescope in Hawaii turned its Gemini multi-object spectrograph toward the comet, now less than 3 weeks from perihelion. At 1/50 astronomical units from the Sun, solar heating had intensified dramatically. The coma glowed brightly, spanning tens of thousands of kilometers, shedding dust and gas at rates measured in hundreds of kilograms per second. The spectroscopic data revealed emission lines from diatomic carbon, CC, molecules fluorescing under solar ultraviolet radiation. This was expected. Ca is a common comet species, produced when carbon-bearing compounds break down under sunlight. It emits characteristic green light at wavelengths around 517 nanometers, giving many comets their distinctive greenish hue. But the intensity was wrong. The brightness of Ci emission depends on how much solar energy the molecules absorb and how efficiently they radiate it away. For typical comets, the relationship between solar distance, Ci production rate, and fluorescence brightness is well characterized. At 1.50, with 3I Atlas's estimated nucleus size and activity level, the CEI emission should have been moderate, visible, diagnostic, routine. Instead, it blazed. The spectral flux in the CI band exceeded model predictions by a factor of 3. That meant either 3 times more Ci molecules were present, or the molecules were fluorescing 3 times more efficiently, or some combination of both. 3 times more Ci molecules could be explained if carbon-rich ices were sublimating at unexpectedly high rates. Given the already anomalous co-dominance, perhaps 3A Atlas's carbon inventory was simply larger than assumed. Models could be adjusted. But 3 times more efficient fluorescence? That required the molecules to be in an excited state, beyond what solar UV alone should induce. Fluorescence efficiency depends on the energy levels molecules occupy before absorbing sunlight. In thermal equilibrium, most molecules sit in their ground state, and fluorescence brightness is determined by how many photons they absorb and re-emit. If molecules are pre-excited, already occupying higher energy levels before solar photons arrive, they can cascade through multiple transitions, emitting more light per absorbed photon. Pre-excitation typically requires an external energy source beyond solar radiation. Impacts with high-energy particles. Electron bombardment in a magnetized environment. Exothermic chemical reactions releasing energy into molecular vibrations. Or confinement in a region where energy densities exceed ambient values, such as within a cavity, a jet channel, or a structured emission region. None of these mechanisms naturally occur in free-expanding cometary comas. Once gas vents from the nucleus, it expands into vacuum, cools adiabatically, and reaches thermal equilibrium with the solar radiation field. There is no mechanism to sustain energy confinement or drive non-thermal excitation across the spatial scales observed. Yet, the data showed enhanced emission across hundreds of thousands of kilometers, far too large for localized hotspots or transient outbursts to explain. Dr. Rajiv Patel, a spectroscopist at the University of Hawaii, ran the numbers multiple times, checking calibrations, reprocessing raw data, searching for instrumental effects that could mimic enhanced emission. He found none. The signal was real. In an email to colleagues, he wrote, "Either we're misunderstanding CE fluorescence in ways that would require rewriting textbooks, or something is pumping energy into these molecules after they leave the nucleus. I don't know which possibility bothers me more." The phrase exotic ice began appearing in internal discussions. The term was deliberately vague, a placeholder for ice compositions we haven't seen before. If 3I Atlas formed in a protoplanetary disk with different chemistry, higher carbon to oxygen ratios, enhanced nitrogen content, or trace metals alloyed into ice matrices, then sublimation might release molecules in unusual energy states. But exotic ice explained nothing. It was a label, not a mechanism. Saying the ice is exotic is like saying the data is anomalous. It restates the observation without providing insight. Some researchers proposed clathrate structures, ice cages trapping volatile molecules under pressure. When clathrates destabilize and release trapped gases, the expansion can be violent, potentially heating molecules through adiabatic compression before they vent into space. This could produce pre-excited species capable of enhanced fluorescence. The idea was plausible. Clathrates exist in solar system comets, particularly in objects originating from cold, outer regions where gases can be trapped during ice formation. If 3 Atlas's formation environment favored clathrate production, its outgassing might differ from typical comets. But clathrate models predicted transient bursts, rapid, explosive releases followed by quiescence, as pressure equilibrated. The enhanced CEI emission in 3A Atlas was sustained, persisting across multiple observation nights as the comet rotated and different regions came into sunlight. A sustained emission required a sustained energy source. Clathrates could not provide that unless new clathrate-rich terrain continuously rotated into view, outgassing with precise timing to maintain constant brightness. Possible, but it required invoking a surface covered uniformly in unstable clathrates, a surface composition with no known analog in observed comets. Another hypothesis focused on carbon chain molecules, complex organic species that could store energy in vibrational modes and release it gradually through cascading molecular transitions. If 3I Atlas's coma contained large, carbon-rich polymers breaking down into smaller fragments, the fragmentation process might release energy into the CII molecules, boosting their fluorescence. This was chemically plausible. Laboratory experiments on irradiated organics had demonstrated that complex carbon chains can undergo photodissociation, releasing daughter molecules in excited states. The challenge was scale. Producing enough excited Ci to account for the observed brightness required a vast reservoir of parent molecules, continuously fragmenting across the entire coma. Models were built, parameters were adjusted, and once again, the models could fit the data, but only by assuming properties that had no independent confirmation. By mid-October, an uncomfortable thought had begun circulating in private. What if the emission was not from cometary outgassing at all, but from something else? This thought was not developed in published papers. It appeared in late-night conversations, in speculative asides during conference calls, in the careful silences that followed someone suggesting a mechanism without naming it. The term non-natural excitation appeared once in an internal draft report circulated among Gemini Observatory researchers. The phrase was deleted before the report's public release. When asked why, the principal investigator responded, "Because we have no evidence for non-natural processes, and including that phrase without evidence would be irresponsible." Fair enough. Science requires evidence, not speculation. But the deletion also reflected a deeper tension, the boundary between cautious interpretation and self-censorship. When does responsible skepticism become a refusal to acknowledge patterns that don't fit comfortable categories? When does avoiding speculation become avoiding difficult questions? The researchers observing 3I Atlas walked this line daily. They were trained to seek natural explanations, to exhaust conventional possibilities before invoking extraordinary ones, to recognize that most anomalies resolve with better data. This training served science well. It prevented premature conclusions, protected reputations, and ensured that published findings met rigorous standards. But it also created blind spots. If an observation genuinely did not fit existing categories, if it represented something new, something not anticipated by models built on solar system experience, then the process of exhausting conventional explanations could delay recognition of that novelty for months or years. And if the object was transient, like 3I Atlas, that delay meant the opportunity to gather decisive data might pass before the community reached consensus that decisive data was needed. Meanwhile, the carbon kept glowing. The emission persisted. And as 3 Atlas approached perihelion, dropping below 1440, on October 15th, it vanished behind the sun's glare. For the next 2 weeks, Earth-based observations ceased. The comet rounded perihelion on October 29th, reaching its closest approach to the Sun, 130 million miles, just outside Mars's orbit, at the exact moment when it was unobservable from Earth. Some data would come from solar observatories. NASA's Solar and Heliospheric Observatory, SOHO, positioned at the Lone Lagrange point, had instruments that could detect comets passing through its field of view. SOHO's coronagraph would capture 3I Atlas as a faint streak, measuring how its coma interacted with the Sun's corona and providing constraints on mass loss rates. But SOHO was designed to study the Sun, not comets. Its spatial resolution and spectroscopic capabilities were optimized for coronal physics, not cometary chemistry. The data would be useful but limited. Snapshots, not comprehensive observations. When 3I Atlas emerged from conjunction in early November, researchers would see the aftermath of perihelion, the comet's brightness, coma size, tail structure, and spectral properties after surviving maximum solar heating. They would infer what happened during the hidden weeks by comparing pre-perihelion and post-perihelion states. But inference is not observation. And some processes, fragmentation events, outburst timing, structural changes in the nucleus, leave ambiguous traces. If something unusual occurred during perihelion, it might be impossible to reconstruct from post-conjunction data alone. Dr. Patel, reflecting on the carbon emission mystery in his observation logs, wrote, "We saw enhanced emission on October 8. We won't see the comet again until November 1st. If the emission increases further, if it shifts wavelength, if it stops abruptly, we won't know. We'll have a before snapshot and an after snapshot, and we'll be left arguing about what happened in between. This is not how I wanted to study the third interstellar object." As October 15th arrived and 3I Atlas slipped behind the Sun, telescopes around the world logged their final observations until emergence. The data was archived, processed, and analyzed. Papers were drafted, describing the carbon emission anomaly in careful language that avoided definitive conclusions. And deep in the metadata of those observations, in the notes appended to spectra and light curves, researchers recorded their uncertainties, the questions they wanted to answer but couldn't, the follow-up observations they'd planned but couldn't schedule, the nagging sense that something important was happening, and they were watching it through a keyhole. The carbon glowed. The explanations strained. And the comet moved into silence. This is not science fiction. This is October 2025. Chapter 6, October 29th, 2025. The Data Gap Week. Perihelion occurred at 1437 UTC on October 29th, 2025. At that moment, 3I Atlas reached its closest point to the Sun, 1.36 astronomical units, 130 million miles, just outside the orbit of Mars. No one saw it happen. From Earth's perspective, the comet was less than 6 degrees from the Sun, well within the exclusion zone where pointing telescopes risks permanent detector damage from scattered solar light. Hubble, Webb, and ground-based observatories maintained their mandated safety margins. For 7 days surrounding perihelion, 3 Atlas existed in observational limbo, hidden by the very star whose energy drove its activity. But SOHO watched. The Solar and Heliospheric Observatory, stationed 1.5 million kilometers from Earth at the gravitationally stable Lone Lagrange point, kept continuous watch on the Sun's corona using its LASCO C3 coronagraph. The instrument blocked the Sun's direct light with an occulting disk, revealing the faint structures of the corona and any objects passing nearby. On October 28th, a faint smudge appeared in SOHO's field of view, 3IS entering from the lower left quadrant, moving at several degrees per day against the background stars. Over the next 36 hours, it traced an arc across the coronagraph's view, brightening as solar heating intensified, then dimming as it receded on the outbound leg of its trajectory. The images were grainy, low resolution, challenging to process. Comets in SOHO data typically appear as faint streaks requiring careful background subtraction to distinguish from coronal streamers, cosmic ray hits, and instrumental noise. But 3 Atlas was visible. Just barely. Analysis of the SOHO images revealed several key findings. First, the comet survived. Some comets, particularly small, fragile ones making close solar passes, disintegrate under thermal stress, their nuclei fracturing and vaporizing within hours of perihelion. 3 Atlas remained intact. Its coma persisted, its brightness decreased smoothly as it receded, and there was no evidence of catastrophic fragmentation. This was expected, given the comet's estimated size. A nucleus several kilometers across should easily withstand heating at 1.36 OIR6. The confirmation was reassuring but not surprising. Second, the coma structure changed. Pre-perihelion observations showed a relatively symmetric dust coma with the anomalous sunward antitail. In SOHO's post-perihelion images, the coma appeared more elongated, stretched along the orbital path, suggesting increased dust production and more rapid expansion velocities. This, too, was expected. Perihelion triggers peak outgassing, releasing dust that forms extensive tails. The change in morphology was consistent with standard cometary behavior under maximum solar heating. Third, and most intriguing, brightness variations occurred during perihelion passage. SOHO captured images at 6-hour intervals, creating a time-lapse of 3 in Atlas crossing the coronagraph's field. Between October 28th at 18:00 UTC and October 29th at 6:00 UTC, a 12-hour span covering the closest approach, the comet's brightness fluctuated by approximately 30%. It brightened, dimmed, brightened again, following no obvious pattern related to solar distance. Brightness variations in comets are common. Rotating nuclei expose different surface areas to sunlight, creating periodic brightness changes. Outbursts, sudden releases of trapped gas, cause transient flares. Changes in viewing geometry alter how much sunlight reflects toward Earth. But 3 Atlas's brightness variations during perihelion did not match the established 16.16-hour rotation period. The fluctuations occurred on timescales of hours, not the expected iron 16-hour cycle. They also did not correlate with changes in solar distance. The comet brightened and dimmed even as its heliocentric distance varied monotonically. This suggested that the variations were intrinsic, not geometric. Something on or within the nucleus was changing its activity level independently of rotation and solar heating. Dr. Carl Badams, a cometary scientist at the Naval Research Laboratory, who specializes in analyzing SOHO data, processed the images and noted the irregularities in his preliminary report. He wrote, "The brightness variations are real and significant. Interpreting them is another matter. We're seeing the comet from an unfavorable angle, through the sun's corona with low spatial resolution. Attempting to attribute specific physical processes to these variations would be premature." He was right. SOHO's data was invaluable but limited. The images confirmed survival and documented morphology changes, but they lacked the resolution and spectroscopic capability to diagnose why the brightness varied or what physical processes were responsible. Meanwhile, outside SOHO's field of view, 3E Atlas continued evolving. Models predicted peak carbon dioxide outgassing during perihelion, temperatures high enough to sublimate ice at maximum rates. If the comet's composition was Kawa-dominated, as August observations suggested, then perihelion should have been the moment of most dramatic activity. But no instruments measured it directly. No spectrographs captured emission lines. No high-resolution cameras imaged the nucleus at closest approach. The most scientifically critical phase of the entire apparition occurred in the observational blind spot created by the sun's proximity. When 3I Atlas emerged from solar conjunction on November 1st, researchers would see the outcome. A comet that had passed perihelion and was now receding, its peak activity over, its behavior in the crucial hours unobserved. This gap was inevitable. Orbital mechanics created it, but its implications were profound. If the comet fragmented during perihelion, the first evidence would appear only after emergence, when multiple brightness peaks indicated separate pieces diverging. If it underwent a massive outburst, the aftermath, expanded coma, enhanced dust production, would be visible post-conjunction, but the outburst itself would be missed. If its trajectory changed due to non-gravitational forces, the deviation would be measurable only after weeks of post-perihelion astrometry accumulated enough data to detect the shift. In each scenario, researchers would be left inferring causes from effects, reconstructing events from circumstantial evidence, arguing over interpretations without the direct observations needed to resolve ambiguities definitively. Dr. Whitaker, watching the data gap unfold from JPL, reflected in her private notes, "We spend billions on telescopes, train for decades, build models refined over centuries of cometary science, and then the geometry of the solar system decides we don't get to watch the most important week. It's humbling, also infuriating." The frustration was shared across the community. Not directed at any individual or institution, everyone understood the constraints. The frustration was existential, aimed at the universe itself for arranging orbits, such that the object of greatest interest passed behind the sun at the moment of greatest activity. Some researchers proposed solutions for future encounters. Space-based observatories stationed in solar orbits different from Earth's could maintain line of sight to comets during Earth's conjunction periods. Telescopes at the Sun-Earth, L4 and L5 Lagrange points, 60 degrees ahead and behind Earth in its orbit, would provide complementary viewing angles, eliminating blind spots. But those solutions required missions that didn't exist in 2025. Proposals took years to develop, budgets to secure, spacecraft to build and launch. For 3I Atlas, the infrastructure was not in place. The gap would remain. As October ended, the astronomy community waited. Amateur astronomers monitored the skies, ready to report the comet's reemergence. Professional observatories pre-positioned schedules, allocating the first available dark sky hours to 3I Atlas observations. Spacecraft adjusted pointing plans. Data pipelines prepared for the incoming flood of post-perihelion images and spectra. And in the silence of the data gap, speculation filled the void. Online forums buzzed with predictions. Would 3I Atlas brighten dramatically, confirming it as a gas-rich comet undergoing peak activity? Would it fragment, revealing a fragile structure unable to withstand solar heating? Would it dim unexpectedly, suggesting depletion of volatile ices? Or would it emerge unchanged, raising questions about what powered its pre-perihelion activity if perihelion itself produced no significant enhancement? Each possibility had advocates. Each was consistent with some subset of available data. None could be confirmed until the comet re-entered observable space. October 29th passed. The perihelion moment came and went, unmarked except in orbital calculations and mission logs. SOHO's coronagraph captured its fragmentary glimpses, enough to confirm survival, not enough to diagnose behavior. And 3I Atlas, indifferent to human curiosity, continued its journey. On October 30th, it began moving away from the sun, still hidden behind solar glare, but accelerating outbound, shedding velocity as solar gravity pulled against its motion, carrying momentum from its interstellar origin toward whatever distant region of the galaxy it would reach in 10,000 years. The data gap would last until November 1st. 7 days total. 168 hours, when the third interstellar object ever detected passed through its most revealing phase, unwatched. When it emerged, everything would change. This is not science fiction. This is October 2025. Toy. Chapter 7, November 5, 2025. Odds that keep stacking. On November 1st, 2025, 3I Atlas reappeared in pre-dawn skies, emerging from behind the sun as a magnitude 9.5 object visible through small telescopes. The first post-perihelion observations came from amateur astronomers in Australia and Japan, who captured wide-field images showing the comet against the constellation Virgo. It had changed. The coma was larger, spanning nearly 100,000 kilometers in visible light, compared to roughly 40,000 kilometers before conjunction. The dust tail extended half a degree across the sky, visible in long-exposure photographs as a faint, ghostly streak. And the color had shifted. Before perihelion, 3 Atlas exhibited the typical reddish hue of reflected sunlight off dust grains mixed with carbon chain molecules. After perihelion, it glowed distinctly green. The green color came from diatomic carbon and Ce, fluorescing at 517 nanometers, the same emission seen in enhanced form during the October 8th observations. But now, post-perihelion, the green glow dominated the visible spectrum. Images captured on November 2nd by the Gemini North Telescope showed Ce emission 3 times stronger than before conjunction. The intensity increase matched predictions. Perihelion heating should have sublimated carbon-bearing ices at maximum rates, releasing Ce molecules that fluoresced under sunlight. The green color was expected, diagnostic of carbon-rich comets. What was not expected was the spatial distribution. Instead of a smooth, centrally concentrated emission fading with distance from the nucleus, the CII glow exhibited structure. Bright patches appeared asymmetrically distributed across the coma, some aligned with the sunward anti-tail direction, others perpendicular to it. The emission was not isotropic. It had preferred directions, maintained across spatial scales of tens of thousands of kilometers. This structure persisted across multiple nights. On November 3rd, 4th, and 5th, independent observations from telescopes in Hawaii, Chile, and South Africa confirmed the same asymmetric CI distribution. As the comet rotated with its 16.16-hour period, the bright patches rotated too, but they did not fade or disperse. They maintained coherence, suggesting that whatever was producing enhanced CA emission was not transient outgassing but a sustained, structured process. Dr. Patel, analyzing the Gemini spectra, ran statistical tests to quantify the asymmetry. The probability that the observed CI distribution could arise from random, isotropic outgassing was less than 0.01, one chance in 100. Something was organizing the emission. Structured emission occurs in comets when jets originate from discrete active regions on the nucleus. As the nucleus rotates, different regions point toward the sun, creating time-variable emission patterns. But those patterns should blur over time as gas and dust expand outward, mix, and thermalize. Maintaining structure across tens of thousands of kilometers required either continuous replenishment from localized sources or some mechanism preventing the usual dispersal. Models invoked magnetic fields, though comets are not typically magnetized. Models invoked electrostatic forces, though the plasma environment around comets is not conducive to large-scale charge separation. Models invoked dust grain properties. Perhaps the CEI molecules were adsorbed onto large dust particles that kept them confined and prevented free expansion. Each model explained the structure. Each required assumptions that had not been independently verified. Each added another adjustable parameter to a growing list of special conditions needed to account for 3 atlases' behavior. By early November, researchers began compiling the full list of anomalies. Hyperbolic trajectory aligned with the ecliptic plane. 3 atlases' orbital inclination relative to the planetary plane was only 5 degrees. The probability of an interstellar object arriving at such a low inclination by chance is approximately 0.2%. Most objects from interstellar space approach from random directions. Alignment with the ecliptic suggests either rare coincidence or, speculatively, targeted approach. Arrival direction near the WOW. Signal origin. The comet's inbound trajectory, when traced backward, pointed to a region of sky within 9 degrees of the famous 1977 WOW signal detected by the Big Ear radio telescope. The probability of this alignment occurring randomly is roughly 0.6%. Sunward anti-tail persisting across millions of kilometers. The jets aimed toward the sun, observed in July and August, maintained collimation over distances where radiation pressure should have dispersed them. No standard dust dynamical model reproduced this without invoking unverified surface properties or internal energy sources. Non-gravitational acceleration inconsistent with standard outgassing. The measured acceleration required mass loss rates or thrust efficiencies that did not match the comet's observed brightness and estimated size. Reconciling the acceleration with thermal models required surface areas or volatile compositions at the extremes of plausible parameter space. Carbon dioxide to water ratio of 8:1, among the highest ever measured, suggesting formation in an environment with radically different chemistry than solar system comets. While possible, such environments are poorly understood, and no direct analogs exist in observed objects. Nickel emissions without iron. Spectroscopy showed strong nickel lines and no detectable iron, violating the typical cosmic ratio of nickel to iron of roughly 1:16. Selective volatilization could explain this, but required invoking nickel compounds with sublimation temperatures distinct from iron, compounds not typically found in comets. Enhanced CEA fluorescence. The diatomic carbon emission brightness exceeded model predictions by factors of 2 to 3, suggesting non-thermal excitation mechanisms. No standard cometary process provides the required energy input at the observed distances. Structured CEI emission, persisting post-perihelion, the asymmetric, coherent green glow, observed in early November, defied expectations for dispersive outgassing. Maintaining structure across 50,000 kilometer scales required organized, sustained processes. Brightness variations during perihelion, uncorrelated with rotation. SOHO data showed fluctuations on timescales shorter than the rotation period, suggesting intrinsic activity changes independent of which surface regions were illuminated. Mass estimate exceeding 33 billion tons. Measurements of the non-gravitational acceleration, combined with estimates of outgassing rates, implied a nucleus mass 3 to 5 orders of magnitude greater than Oumuamua or Borisov. This made 3I Atlas statistically unlikely. Delivering such a massive object to the inner solar system from interstellar space requires either rare coincidence or a different origin mechanism than random ejection from another star system. Each anomaly, in isolation, had potential explanations. Unusual chemistry. Rare but natural compositions. Exotic ices. Complex surface topography. Geometric coincidences. Measurement uncertainties. But these anomalies did not appear in isolation. They appeared together in the same object, compounding into a profile that did not match any known comet class. Statistical independence matters. If 10 independent anomalies each have a 1% chance of occurring, the compounded probability of all 10 appearing together is 0.0 on 10, 1 in 1020, or 1 in 100 quintillion. Of course, the anomalies were not entirely independent. Some correlated. A high Kabataho ratio naturally leads to unusual outgassing behavior, which affects non-gravitational acceleration. Enhanced CEI emission correlates with carbon-rich compositions. But even accounting for correlations, the joint probability of the observed anomalies co-occurring by chance was extraordinarily low. Dr. Avi Loeb, writing on Medium on November 5, calculated a rough joint probability. If we conservatively estimate that each major anomaly has a 1 in 50 chance of occurring naturally, and if we have 10 such anomalies with partial correlations, reducing the effective count to 6 independent factors, the joint probability is 1/5006, or roughly 1 in 15 billion. That does not mean 3I Atlas is artificial. It means that if it is natural, it represents a comet type we have never encountered before, formed under conditions we do not understand, exhibiting behaviors we cannot model with existing physics. He continued, when faced with extremely low probability natural explanations, we are obligated to consider alternative hypotheses. Not because aliens are likely, but because ignoring statistically improbable natural scenarios is equally unscientific. The null hypothesis, this is just a comet, must be tested against the data, not assumed a priori. The response from the broader community was swift and divided. Some agreed that the accumulated anomalies warranted re-examining assumptions. Perhaps interstellar comets were fundamentally different from solar system comets, shaped by environments humanity had never sampled. Perhaps 3 Atlas represented a new class of object. Primordial material from the early galaxy, ices formed in molecular clouds, or fragments of disintegrated planets from other systems. Others argued that invoking low probabilities was misleading. The universe is large. Rare events happen. Encountering one unusual comet in a sample size of 3 interstellar objects was not statistically significant. After all, Oumuamua had also been anomalous, exhibiting non-gravitational acceleration that took years to explain. Anomalies are features of discovery. They appear because our models are incomplete, not because the objects are extraordinary. The debate played out in journal comment sections, conference calls, and increasingly public forums. Media outlets picked up on the controversy. Headlines ranged from measured, scientists debate origin of unusual comet, to sensational, is 3 Atlas an alien probe? Harvard scientist says maybe. The attention created pressure. Researchers found themselves navigating not just scientific questions, but public perception, funding implications, and reputational risks. Publishing speculation without definitive evidence could damage careers. But refusing to acknowledge anomalies that didn't fit models could delay recognition of genuinely new phenomena. It was an uncomfortable position. Science values both skepticism and openness. But applying those values to a fast-moving, once-in-a-lifetime event with compounding anomalies tested the community's ability to balance caution with curiosity. By November 5th, the positions were clear. Some researchers argued for conservative interpretation, exhaust natural explanations first, gather more data, avoid premature conclusions. Others argued for expansive hypothesis space, consider all possibilities including low-probability ones, and let evidence arbitrate. Both positions were scientifically defensible. Both reflected legitimate concerns about rigor and reputation. And both recognized that December 19th, the closest approach to Earth, the final high-resolution observation window, was 6 weeks away. Whatever 3I Atlas was, the clock was running out. This is not science fiction. This is November 2025 away. November 15th, 2025. Who decides what we can say? On November 15th, 2025, a draft press release circulated among NASA's communications team at headquarters in Washington. The document summarized findings from Hubble, Webb, and ground-based observations of 3E Atlas. intended for public release ahead of the December 19th closest approach. The draft described the comet's interstellar origin, its unusual carbon dioxide dominance, and the ongoing spectroscopic campaigns characterizing its composition. It mentioned non-gravitational acceleration and noted that models were being refined to account for the observed behavior. Then, buried in the fourth paragraph, appeared a sentence that would be deleted before publication. While current data are most consistent with natural cometary processes, the accumulated anomalies have led some researchers to consider whether alternative hypotheses, including technological explanations, warrant investigation. The sentence was carefully hedged. It didn't claim alien technology. It merely acknowledged that some scientists were considering the possibility. It attributed the consideration to some researchers, not to NASA itself. It described this as worthy of investigation, not as a conclusion. But it was deleted. The deletion sparked a week-long internal debate about language, responsibility, and the boundaries of scientific communication. The debate was not about censorship. No one was forbidden from speaking. It was about institutional messaging. What should NASA, as an organization, say publicly about an object whose nature remained uncertain? The arguments for deletion were straightforward. NASA is a government agency accountable to Congress, the White House, and the public. Its statements carry weight, suggesting, even obliquely, that an interstellar object might be technological would trigger intense media scrutiny, public speculation, and political questions. If subsequent data revealed a mundane explanation, if 3I Atlas turned out to be an unusual but natural comet, the agency would face criticism for fueling unfounded speculation. Moreover, the scientific consensus was not settled. Most researchers studying 3I Atlas still favored natural explanations, even if those explanations required invoking rare conditions. Highlighting minority views in an official press release could misrepresent the state of knowledge, implying greater uncertainty than actually existed within the expert community. The arguments for retention were equally compelling. Science progresses by considering multiple hypotheses and testing them against evidence. If some researchers genuinely believed that technological origins could not be ruled out based on available data, then, acknowledging that consideration, which was transparency, pretending the debate didn't exist, served no one. Furthermore, the public was already aware of the controversy. Avi Loeb's Medium essays had been widely circulated. News outlets were covering the anomalies. Social media buzzed with theories, ranging from scientifically informed to wildly imaginative. NASA's silence on the technological hypothesis would not prevent discussion. It would simply remove the agency's voice from a conversation happening with or without its participation. The compromise was semantic. The final press release, published on November 18th, included this language: 3 Atlas exhibits properties that challenge existing models of interstellar comets. Researchers are exploring a range of hypotheses to explain the observations, and data collection will continue through the December close approach. The phrase range of hypotheses implied diversity, without specifying what those hypotheses were. It was factually accurate, diplomatically vague, and satisfied no one. Critics within NASA's astrophysics division felt the revision was evasive. Dr. Sean Domagal-Goldman, acting director of the division, wrote in an internal email, "We're not hiding anything. All the data is public. Papers are being published. Researchers can say whatever they want in their own work. But when NASA makes a statement, we represent the consensus view, not the outliers. If consensus shifts, our messaging will shift. Until then, we describe what most experts believe, which is that this is a natural object." Critics outside NASA felt the agency was being overly cautious. Dr. Jason Wright, an astronomer at Penn State University who studies technosignatures, argued in a blog post, "The problem with consensus view is that consensus lags evidence. Consensus forms after anomalies are resolved, not while they're being investigated. By the time consensus acknowledges something unusual, the opportunity to gather decisive data may have passed." NASA should be describing the full scientific process, including the consideration of low probability hypotheses, not just the majority opinion. Both perspectives had merit. Both reflected legitimate concerns about credibility, public understanding, and scientific integrity. Meanwhile, individual researchers navigated their own versions of this tension. Dr. Patel, whose spectroscopic work had documented the enhanced CIA mission, submitted a paper to the Astrophysical Journal Letters on November 10. The manuscript presented the data, described the fluorescence anomaly, and proposed several natural mechanisms: cloth rate outgassing, carbon chain photodissociation, and dust grain shielding. In the discussion section, he included a paragraph noting that the required energy inputs for enhanced fluorescence might indicate processes not yet cataloged in cometary science. A reviewer suggested deleting the paragraph, commenting, "This is vague and adds no scientific value. Either propose a specific mechanism or omit the speculation." Patel rewrote the paragraph, making it more specific. The sustained, non-thermal excitation implied by the observed fluorescence could result from localized heating via exothermic chemical reactions, electrical discharge in ionized gas jets, or confinement effects in structured emission regions. Alternatively, if the emission originates from a source other than passive cometary outgassing, further observations at higher spatial resolution are required to identify the mechanism. The revised paragraph passed review. It was still speculative, but it framed the speculation in testable terms, mechanisms that future observations could confirm or rule out. This was acceptable. Science allows speculation if it generates predictions. But Patel knew the subtext. A source other than passive cometary outgassing was code for something we don't understand, and maybe don't expect in a comet. The phrase was careful, defensible, and utterly opaque to anyone not steeped in the literature. This was the language of scientific caution, precise, hedged, and often inaccessible. It served a purpose: protecting researchers from overreach, maintaining standards of evidence, ensuring that published claims could withstand scrutiny. But it also obscured. A lay reader encountering Patel's paper would see jargon about fluorescence, cloth rates, and exothermic reactions. They would not see the underlying question: why is this comet glowing brighter than it should? And what does that mean? The gap between what scientists wrote and what the public understood created space for misinformation. Online forums filled with interpretations of 3I Atlas, ranging from informed analysis to conspiracy theories. Some claimed NASA was covering up evidence of alien technology. Others dismissed the anomalies entirely, asserting that scientists were chasing noise. Both extremes misrepresented the actual state of knowledge, which was neither cover-up nor dismissal, but genuine uncertainty navigated through careful, incremental investigation. Dr. Domagal Goldman addressed this gap in a public webinar on November 16, hosted by NASA's Astrophysics Division. Speaking to an online audience of thousands, he explained, "Science is not a process of certainty. It's a process of reducing uncertainty. When we encounter something we don't fully understand, we build models, test predictions, gather more data. Sometimes the answer is mundane. Sometimes it's surprising. But the process requires patience. Jumping to conclusions. Either it's definitely aliens or it's definitely not shortcuts the investigation. Right now with 3 Atlas, we're in the investigation phase. We have anomalies. We have hypotheses. We don't have final answers." He continued, "And that's okay. That's how discovery works. What's important is that we're transparent about what we know, what we don't know, and what we're doing to find out. You'll see papers published with conflicting interpretations. You'll see scientists disagreeing. That's not failure. That's science functioning correctly. The answer will emerge from that process, not from any single press release or headline." The webinar was well received. It contextualized the uncertainty, explained the scientific method, and de-escalated some of the more sensational narratives circulating online. But it also highlighted a structural problem. Scientific communication operates on timescales incompatible with fast-moving events. Peer review takes months. Consensus forms over years. Press releases are vetted through multiple approval layers. By the time official statements reflect the state of knowledge, the state of knowledge has often moved on. For 3A Atlas, this mismatch was acute. The object was approaching its closest point to Earth. Every week brought new observations. Models updated constantly. The cutting edge of understanding existed in preprint servers, conference presentations, and informal discussions, not in the polished, peer-reviewed literature that official communications drew from. So the public saw a fragmented picture. Sensational headlines, cautious press releases, preprint papers with technical jargon, and passionate debates on social media. Navigating this landscape required either expertise or trust, and trust was strained when official statements seemed to lag behind obvious questions. On November 15th, while NASA's communications team debated language, 3 Atlas continued its journey. It was now 1.9 astronomical units from the Sun, receding outbound at 140,000 miles per hour. Its brightness had stabilized at magnitude 9.2, making it a consistent target for professional and amateur observers alike. And it continued to accelerate non-gravitationally at rates slightly higher than predicted by updated models. Davide Farnocchia at JPL revised the ephemeris again on November 14th, incorporating 2 more weeks of post-perihelion astrometry. The new orbital solution showed a persistent residual acceleration of approximately 310 meters per second squared. Small, but measurable, and consistent across independent observation sets. He noted in the JPL Horizons Update log, non-gravitational acceleration remains statistically significant. Magnitude and direction compatible with a symmetric outgassing, though required outgassing geometry remains unconstrained by direct imaging. Further observations recommended. Translation. The comet was still accelerating in ways that didn't perfectly match models, and no one had directly seen the surface features that would explain it. By mid-November, the scientific community had settled into an uneasy equilibrium. Data accumulated. Models improved incrementally. Debates continued, respectful but pointed. And everyone focused on December 19th, the date when Earth, 3I Atlas, and the Sun would align such that observing geometry maximized spatial resolution, when the closest approach would provide the clearest images, the sharpest spectra, the best chance to resolve ambiguities. 5 weeks remained. The countdown had begun. But beneath the scientific routine, observations, analysis, publication, was a quiet acknowledgement that the language used to describe 3 Atlas mattered. Not because language changed the physics, but because language shaped what questions were asked, what observations were prioritized, what hypotheses were considered legitimate. If you call something an unusual comet, you investigate it as a comet. If you call it an object of unknown origin, you expand the investigation. The difference is subtle, but consequential. And in November 2025, as 3I Atlas glowed green against the stars, the question of what to call it, and who decided, remained unresolved. This is not science fiction. This is November 2025 Dartoy. Chapter 9, November 22nd, 2025. The Alignment Window. 1,1600 words. On November 22nd, 2025, a rare geometric configuration occurred. For approximately 18 hours, 3I Atlas, Earth, and the bright star Regulus in the constellation Leo aligned within a narrow angular corridor, creating an opportunity for precision polarimetry, measurements of how light waves oscillate as they traveled us through the comet's coma. Polarimetry reveals structure, invisible to standard imaging. Unpolarized sunlight scatters off dust grains in the coma, and the scattering process imparts polarization depending on grain size, shape, and composition. By measuring the degree and angle of polarization, researchers can infer dust properties, whether grains are spherical or irregular, fluffy or compact, pristine or processed. But polarimetry requires careful calibration. You need a bright reference star near the comet to subtract instrumental effects and atmospheric contributions. Regulus, a magnitude 1.4 star, was ideal. And on November 22nd, it passed within 2 degrees of 380 Atlas, close enough for simultaneous observation by telescopes with wide fields of view. The Nordic Optical Telescope in the Canary Islands dedicated 6 hours to polarimetric observations. The Southern African Large Telescope contributed 4 hours. Together, they captured polarization maps spanning the entire visible coma, from the bright central condensation near the nucleus out to the faint outer edges 80,000 kilometers away. The data revealed structure. In typical comets, polarization increases smoothly with distance from the nucleus as dust grains separate and sunlight scatters at different angles. The polarization curve follows predictable patterns based on grain size distributions, usually peaking at phase angles, the Sun-Comet-Earth angle, around 90 degrees. 3I Atlas's polarization curve was not smooth. At distances less than 10,000 kilometers from the nucleus, polarization was low, near zero, indicating either very small grains, submicron size, or very large particles, millimeters or larger. Both extremes produce minimal polarization because small grains scatter light nearly isotropically, while large particles create complex, multi-angle scattering that averages out. Between 10,000 and 40,000 kilometers, polarization spiked to 12%, significantly higher than typical comets at this phase angle. High polarization indicates elongated, irregular grains preferentially aligned or scattering at angles that enhance polarization. Beyond 40,000 kilometers, polarization dropped abruptly back to 3%, remaining constant to the edge of the measurable coma. This three-region structure, low, high, low, had no obvious explanation. Dr. Olga Ivanova, a cometary dust specialist at the Astronomical Observatory of Taras Shevchenko National University in Ukraine, led the polarimetry analysis. She compared 3I Atlas's polarization profile to a database of 200 comets observed over the past 40 years. None matched. Most comets showed monotonic increases in polarization with distance, leveling off at outer coma regions. Some showed double-peak structures due to multiple dust populations ejected at different times. But the sharp transitions in 3I Atlas, the spike and subsequent drop, suggested spatial segregation of dust types at specific distances. Spatial segregation occurs when different-sized grains separate during ejection due to differing responses to radiation pressure. Small grains are pushed outward faster, creating a radial gradient. But this process is gradual, not abrupt. The sharp polarization spike at 10,000 kilometers and drop at 40,000 kilometers implied boundaries, discrete transitions rather than smooth gradients. One explanation invoked episodic outbursts. If the comet had experienced a sudden release of fine dust 12 hours before the observations, and then a subsequent release of large particles 6 hours later, the dust populations might not yet have mixed, creating spatial layers detectable in IMS polarization maps. But timing this to coincide exactly with the Regulus alignment when polarimetry was possible required coincidence. Possible, but unlikely. Another explanation focused on the sunward antitail jets. If those jets contain dust with unusual properties, perhaps carbon-rich particles or grains with metallic inclusions, the polarization signal might differ from typical silicate dust. The jets could create regions of distinct polarization, especially if they maintained collimation, as observed. This hypothesis was testable. Polarimetry at different wavelengths could distinguish silicate grains, which polarize similarly across the visible spectrum, from carbonaceous or metallic grains, which exhibit wavelength-dependent polarization. Multi-wavelength observations were planned for late November, but required additional telescope time not yet secured. A third, more speculative explanation considered that the polarization structure reflected not just dust properties, but organized emission. If the coma contained regions where particles were confined, by magnetic fields, by electrostatic forces, or by structured outgassing, those regions might exhibit coherent polarization signals. Magnetic fields in comets are weak, typically inherited from the interplanetary medium rather than generated internally. Strong enough fields to confine dust over thousands of kilometers would require plausibly large currents or impossibly strong magnetization. Electrostatic confinement faced similar problems. While dust grains in cometary comas can become charged by solar UV radiation and electron impacts, the net charge is usually small, and electric fields dissipate quickly in the tenuous plasma environment. Sustaining confinement over 30,000 kilometer scales would require continuous charging mechanisms not observed in any comet. Yet the data showed boundaries, sharp transitions that seemed to define regions rather than gradual mixing zones. Dr. Ivanova, summarizing her findings in a presentation to the European Planetary Science Congress on November 24, concluded, "The polarization profile of 3 Atlas is unprecedented. We can model it with multi-component dust populations, but the required spatial segregation and timing are contrived. Either this comet experienced a highly unusual sequence of outbursts immediately before our observations, or the dust dynamics are fundamentally different from what we understand." She paused, then added, "Or there is structure in the coma that we do not yet have the physical framework to describe." That last sentence, ambiguous, carefully phrased, captured the discomfort many researchers felt. The data was clear. The interpretations were not. Every model that fit the polarization profile required invoking special circumstances or unexplained mechanisms. Meanwhile, the same geometric alignment that enabled polarimetry also allowed high-resolution spectroscopy. The Keck Observatory in Hawaii, using its high-resolution eggshell spectrometer, HIRES, obtained spectra with resolving power RGG 36,000s, sufficient to detect not just emission lines, but their shapes, widths, and velocity structures. The spectra revealed something unexpected. The emission lines were narrower than predicted. Spectral line width reflects the velocity distribution of emitting atoms. In a comet, gas molecules leave the nucleus at thermal speeds hundreds of meters per second, plus any bulk flow velocities from jets up to a few kilometers per second. The combination produces emission lines broadened by Doppler shifts. Red shifted light from molecules moving away, blue shifted light from molecules approaching. Typical cometary emission lines have full width half maximum, FDFOM, values of 2-4 km/s, reflecting the spread of velocities in the expanding coma. 3. Atlas's CI emission lines measured 0.9 km/s FDFOM, less than half the typical width. Narrow lines mean low velocity dispersion. The molecules were moving in more organized, less chaotic flows than expected. This suggested either very cold gas, unlikely given solar heating, or highly collimated jets, possible, but requiring a degree of organization not typically seen. Further analysis revealed that the narrow lines were not uniform across the coma. Near the nucleus, emission lines were broader, around 2 km/s, consistent with standard outgassing. But in the outer coma, particularly in regions coinciding with the sunward jets, the lines narrowed to 0.71 km/s. This gradient, from broad near the nucleus to narrow far away, inverted the usual pattern. Normally, coma gas expands, cools, and broadens as it moves outward, and collisions between molecules cease. In 3I Atlas, something was maintaining or increasing the organization of molecular motion as gas moved away from the nucleus. One hypothesis invoked adiabatic cooling. If the gas expanded very rapidly, it could cool efficiently, reducing thermal velocities and narrowing emission lines. But this would require expansion speeds significantly higher than observed in 3I Atlas's brightness and dust production. Another hypothesis suggested that the narrow lines came from recondensation, gas molecules temporarily refreezing onto dust grains and then resublimating in the outer coma. This could reset velocity distributions, creating localized populations with low dispersion. But recondensation typically occurs only in extremely dusty environments, and 3 Atlas's dust-to-gas ratio, while elevated, was not extreme. A third hypothesis, mentioned in private but not published, wondered whether the organized velocity structure indicated something other than random outgassing. If the coma contained directed flows, streams of gas moving coherently rather than expanding chaotically, the emission lines would naturally narrow in those regions. Directed flows occur in jets, but jets are localized. To produce narrow emission lines across thousands of kilometers, the flows would need to maintain directionality far beyond where collisional interactions should have randomized velocities. By the end of November 22, the alignment window closed. Regulus moved out of favorable geometry. The polarimetry and spectroscopy data were archived, and researchers began the months-long process of detailed analysis. But the preliminary findings added to the growing list: polarization boundaries at 10,000 and 40,000 kilometers, narrow emission lines in the outer coma dot, velocity structures suggesting organization rather than chaos. Each finding individually strained, but did not break standard cometary models. Together, they painted a picture of an object that operated near the edge of what current theory accommodated. Always explainable, always unusual, always demanding another special assumption. Dr. Ivanova, in her notes following the FCC presentation, wrote, "In 40 years studying comets, I have never encountered an object that required so many almosts in describing it. Almost like a typical comet, but with unusual composition. Almost like normal outgassing, but with unexpected structure. Almost within the range of known behavior, but consistently at the extremes. At some point, almost becomes not quite, and we must ask whether our framework is incomplete." November 22nd had provided the clearest look yet at 3 Atlas's fine structure. The data was rich, detailed, unprecedented, and it deepened the mystery. This is not science fiction. This is November 2025. Chapter 10, November 28, 2025. History's Quiet Precedents. On November 28, 2025, a team of researchers at the SETI Institute in Mountain View, California, convened a virtual workshop titled Lessons from Oumuamua and Borisov: What Interstellar Objects Teach Us. The workshop aimed to compare 3 Atlas with the 2 prior interstellar visitors, searching for patterns, commonalities, and instructive differences. The first interstellar object, Oumuamua, had been discovered on October 19, 2017, by the Pan-STARRS telescope in Hawaii. It passed within 0.250 of Earth, much closer than 3I Atlas, but was already outbound when detected, providing only a brief observational window. Oumuamua's defining anomaly was its non-gravitational acceleration, measured at approximately 5010 ms. For years, researchers debated the cause. Outgassing? Possible, but no visible coma or dust trail was detected. Solar radiation pressure? Possible, but required an extremely thin, pancake-like geometry inconsistent with tumbling dynamics. A hydrogen iceberg? Proposed in 2020, requiring the object to be composed of solid molecular hydrogen that sublimated without visible signatures. By 2023, the hydrogen iceberg model had gained tentative acceptance, though direct evidence remained absent. The object was gone, beyond reach of even the most powerful telescopes, leaving only 80 days of observations to analyze for decades. The second interstellar object, Toei Borisov, was discovered on August 30, 2019, by amateur astronomer Gennady Borisov using a homemade telescope. Unlike Oumuamua, Borisov was unambiguously cometary. It had a bright coma, a visible tail, and spectroscopic signatures of water and carbon monoxide outgassing. Borisov's chemistry resembled solar system comets from the Oort cloud, suggesting that comets around other stars might not differ drastically from our own. Its Ko-to-Ocho ratio was elevated, about 1:1, compared to typical ratios of 1. But not wildly anomalous. It exhibited non-gravitational acceleration consistent with outgassing. It was, in most respects, unremarkable, except for its interstellar origin. Borisov reassured the community that interstellar comets could be understood with existing frameworks. Yes, chemistry varied. Yes, some properties fell outside the typical range. But fundamentally, Toei Borisov behaved as expected. Now, 3I Atlas.3. Dr. Seligman noted, if we treat these 3 objects as a statistical sample, we see increasing complexity. Oumuamua challenged our models but provided little data. Borisov validated expectations, but hinted at compositional diversity. 3I Atlas presents multiple, compounding anomalies, each explainable in isolation but collectively straining our framework. The trend suggests that interstellar objects may be more varied than we anticipated based on solar system analogs. Nelly, another participant, Dr. Michelle Bannister from the University of Canterbury in New Zealand raised a cautionary point. Sample size matters. 3 objects is not enough to define trends. For all we know, the next 10 interstellar visitors will all resemble Borisov, and will look back at Oumuamua and 3I, Atlas, as statistical outliers. We must resist over-interpreting limited data. Nim. 1. Fair point. But the workshop also reviewed historical precedents within the solar system, comets that initially appeared anomalous and were later explained. Comet Schwarzmann-Wachmann 1, orbiting between Jupiter and Saturn, exhibits periodic outbursts unrelated to solar heating. It remains active even at 6O, far from where water ice sublimates. The explanation: subsurface reservoirs of highly volatile carbon monoxide and nitrogen, which sublimate at low temperatures. Initially puzzling, eventually understood. Comet Hale-Bopp in 1997 showed unexpected molecular emissions, deuterated water, complex organics, suggesting enrichment in heavy isotopes. Initially surprising, later interpreted as primordial material preserved in the Oort cloud since the solar system's formation. Anomalous chemistry, but natural origin. Comet 67P, Churyumov-Gerasimenko, visited by ESA's Rosetta spacecraft in 2014-2016, revealed a surface far more complex than models predicted. Cliffs, smooth plains, active pits, and layered structures. Rosetta's close-up observations forced revisions of cometary formation theories, but ultimately confirmed natural processes. The pattern was clear. Comets surprise us. They exhibit behaviors not anticipated by models built on limited data. But additional observations eventually integrate those surprises into refined theories. The question for 3 Atlas was whether this pattern would hold. Was it another Schwarzmann-Wachmann or Hale-Bopp? Initially puzzling, eventually understood. Or was it fundamentally different? An object whose anomalies persisted because it represented something outside the cometary framework. Dr. Frank Marquez from the SETI Institute offered a philosophical perspective: science advances by anomaly. Every major paradigm shift began with observations that didn't fit. Stellar spectra that implied atoms, galaxy rotations that implied dark matter, accelerating expansion that implied dark energy. Most anomalies resolve conventionally, but some don't. The challenge is distinguishing between anomaly that needs better models and anomaly that needs new physics. We don't have a reliable algorithm for that distinction. It requires judgment, and judgment is subjective. Whoa. He paused, then added, with 3 Atlas, we're in the ambiguous middle. Not clearly conventional, not clearly extraordinary. The risk of premature conclusions cuts both ways. Dismiss it as just a comet, and we might miss something genuinely new. Call it alien technology without evidence, and we damage the credibility needed for serious investigation. The only path forward is continued observation and epistemic humility. The workshop concluded without consensus. Some participants felt 3I Atlas was a natural comet with unusual but explicable properties. Others felt the accumulation of anomalies justified expanding the hypothesis space to include possibilities not typically considered in cometary science. But everyone agreed on one point: December 19th mattered. The closest approach would provide the highest resolution images, the most detailed spectra, and potentially decisive data to resolve ambiguities. That afternoon, Dr. Seligman compiled a list of critical observations needed during the December 19th window. High-resolution imaging to resolve surface features, search for fragmentation, and measure rotation state changes. Multi-wavelength spectroscopy to constrain dust composition and identify any unusual molecular species. Polarimetry follow-up at different phase angles to test grain models. Radar observations, if feasible, to measure nucleus size and surface properties directly. Astrometry with subarcsecond precision to refine the non-gravitational acceleration and test for any trajectory changes. Each observation required telescope time, coordination across facilities, and clear skies, factors not entirely within researchers' control. As the workshop ended, participants returned to their institutions with renewed focus. December 19th was 3 weeks away. Proposals were submitted for directors' discretionary time on Hubble and Webb. Ground-based observatories finalized schedules. Amateur networks coordinated continuous coverage to catch any unexpected outbursts or brightness changes. But beneath the logistical planning was a quiet acknowledgement. History's precedents provided some comfort, but no guarantees. Oumuamua had come and gone, leaving more questions than answers. Borisov had arrived and departed, validating expectations, but not resolving Oumuamua's mysteries. Now 3I, Atlas was weeks from its final close look. Whatever it was, unusual comet, primordial iceberg, statistical outlier, or something unanticipated, the clock was running out. After December 19th, it would recede beyond Jupiter, fading into the cold and dark, carrying answers that humanity might glimpse but never fully grasp. Dr. Marcus, reflecting in his notes after the workshop, wrote, "Every interstellar object is a visitor from a place we cannot visit, a messenger from stellar environments we observe only from immense distances. They bring data, compositions, structures, behaviors shaped by alien suns and alien disks. If we're lucky, we learn something. If we're wise, we recognize how much we still don't know." The precedents were instructive, the patterns suggestive, the conclusions elusive. And 3 Atlas, glowing green in the constellation Virgo, continued its journey toward the moment when humanity would have its best and last chance to understand. This is not science fiction. This is November 2025. Chapter 11, Can't Rule Out Technology. On December 3, 2025, Japan's X-ray satellite X-RISM captured the first X-ray image of 3I Atlas. The observation lasted 20 hours, using the Extend Soft X-ray Imaging Telescope to map emissions across the comet's coma. X-ray emission from comets is well understood. It occurs through a process called charge exchange. Highly ionized atoms in the solar wind collide with neutral gas molecules in the coma, capturing electrons and releasing energy as X-rays. The intensity depends on solar wind density, comet outgassing rate, and the geometric configuration. Most comets emit soft X-rays in a relatively compact region near the nucleus, extending a few thousand kilometers. 3 Atlas's X-ray emission extended 400,000 kilometers, nearly 250,000 miles. The diffuse X-ray cloud was not centrally concentrated. Instead of peaking at the nucleus and fading outward, the emission was distributed across a vast, irregular region that shifted and pulsed over the 20-hour observation window. The spatial extent was unprecedented, more than 10 times larger than typical cometary X-ray halos. Dr. Kumiko Morihana from JAXA's Institute of Space and Astronautical Science led the analysis. She compared X-RISM's observations with historical X-ray data from comets Hale-Bopp, Linear, and Eisen. None exhibited emissions extending beyond 40,000 kilometers. 3 Atlas's 400,000 kilometer cloud was an order of magnitude larger. What could produce such extended X-ray emission? One explanation invoked unusually high outgassing. If 3I Atlas was releasing gas at rates far exceeding typical comets, the coma would be denser, providing more neutral molecules for charge exchange. More molecules, more collisions, more X-rays, distributed over larger volumes. But the estimated outgassing rates from visible and infrared observations, roughly 70 kJ of Ku, were elevated but not extreme. Comet Hale-Bopp, at peak activity, released water at rates exceeding 10,000 kJ and did not produce X-ray halos approaching 400,000 km/h. Another explanation focused on solar wind conditions. If 3I Atlas happened to be immersed in a particularly dense or energetic solar wind stream during the X-RISM observation, enhanced charge exchange could produce brighter, more extended emissions. Dr. Morihana checked solar wind data from NASA's Advanced Composition Explorer, ACE spacecraft, which monitors conditions at the Lone Lagrange point. On December 3rd, solar wind density was 6 particles per cubic centimeter, slightly above average but not exceptional. Wind speed was 420 km/s, moderate. There was no evidence of a solar storm or coronal mass ejection that could explain a tenfold enhancement in X-ray extent. A third explanation considered the possibility that 3I Atlas's coma contained trace metals, elements with high charge exchange cross-sections that could boost X-ray production efficiency. Nickel, for instance, has electronic configurations that favor X-ray emission when ionized by solar wind. This was speculative but testable. X-ray's spectral resolution could identify emission line energies, revealing which elements were responsible for the X-rays. Preliminary spectra showed oxygen and carbon lines, expected from coho and water, but also hints of nickel lines at 7.5 keV, consistent with highly ionized nickel atoms undergoing charge exchange. The nickel connection was intriguing. Ground-based spectroscopy had already identified anomalous nickel emissions in the visible spectrum. Now, X-ray data suggested nickel was present in ionic form, distributed throughout the vast coma. But nickel's presence, even in elevated amounts, did not automatically explain the 400,000 kilometer extent. The spatial distribution still required either extremely high gas densities or some mechanism confining gas and ions over scales far larger than gravity or magnetic fields could plausibly maintain. Dr. Morihana's preliminary report, circulated to collaborators on December 5, concluded, "The X-ray emission morphology of 3 Atlas is anomalous and not readily explained by standard cometary models. The spatial extent suggests either unprecedented outgassing rates, not reflected in optical observations, or an additional energy source sustaining ionization in the outer coma. Further multi-wavelength observations are essential to resolve this discrepancy." The X-RISM data reached Avi Loeb at Harvard on December 4. He immediately wrote a medium essay titled "First X-ray Detection of 3 Atlas," which went viral within hours. In the essay, Loeb summarized the X-RISM findings and then posed a question. The extended X-ray halo, the nickel without iron composition, the sunward jets maintaining collimation, the non-gravitational acceleration, the structured CE emission anomaly invites conventional explanations. But at what point does the accumulation of anomalies suggest we are not looking at an unusual natural object, but at something designed? He continued, "I am not claiming 3 Atlas is a spacecraft. I am claiming we cannot rule it out based on current data. The scientific method requires considering hypotheses that fit observations, even if those hypotheses are uncomfortable. If the observations are consistent with a technological artifact, whether intentional probe, derelict machinery, or debris from an industrial process, then that hypothesis deserves investigation alongside natural explanations. Dismissing it without evidence is as unscientific as accepting it without evidence." The essay's final paragraph sparked intense reactions. In 2017, we missed the opportunity to study Oumuamua up close because we did not recognize its significance until it was leaving. We have 3 weeks before 3I Atlas reaches closest approach to Earth. If there is even a 1% chance this object is technological, the potential knowledge gain justifies deploying every available instrument. Because if we wait for certainty, the object will be gone, and we will spend decades debating what we should have looked for, but didn't. Well, the response was immediate and divided. Dr. Jason Wright, Penn State astronomer and technosignature researcher, tweeted, "Loeb is right that we can't rule out technology. But can't rule out is not likely. The prior probability for natural explanations is orders of magnitude higher. Yes, investigate thoroughly. But let's not pretend technological origins are equiprobable with cometary origins. They're not." Dr. Paul Sutter, astrophysicist and science communicator, published a rebuttal titled, "Why 3I Atlas is Almost Certainly Not Aliens." He argued, every anomaly Loeb cites has potential natural explanations. Yes, those explanations require invoking rare conditions. But rare conditions occur. The universe is large. Encountering a statistically improbable comet is far more likely than encountering alien technology. Given that we have observed billions of comets and exactly 0 confirmed alien artifacts. Dr. Jill Tarter, former director of the SETI Institute, offered a measured perspective in an interview with Scientific American. The question isn't whether we should investigate, we should. The question is how to frame that investigation. If we approach 3I Atlas solely as a comet, we risk missing signals that fall outside cometary parameter space. If we approach it as potentially technological, we risk wasting resources on false positives. The answer is to remain hypothesis agnostic, collect data comprehensively, analyze rigorously, and let evidence guide conclusions, not preconceptions. She added, "What concerns me is the polarization. People are choosing sides, definitely aliens versus definitely not, before the investigation is complete. Both extremes are premature. Uncertainty is uncomfortable, but it's honest. We don't yet know what 3E Atlas is. We should be comfortable admitting that." Meanwhile, NASA found itself navigating the escalating public interest. On December 6th, the agency held a press briefing featuring Dr. Nikki Fox, Associate Administrator for the Science Mission Directorate, and Dr. Tom Statler, Lead Scientist for Solar System Small Bodies. Dr. Fox opened, "3A Atlas is the third interstellar object detected passing through our solar system, and it has provided an extraordinary opportunity for scientific study. Multiple NASA missions, Hubble, Webb, Swift, and others, have observed the comet, and we've partnered with international observatories to maximize data collection. The object exhibits unusual properties, which is exciting because it offers insights into conditions in other star systems." A reporter asked directly, "Can NASA rule out that this object is artificial?" Dr. Statler responded carefully, "Based on current observations, 3I Atlas exhibits behaviors consistent with cometary activity, outgassing, dust production, and brightness variations explained by solar heating. However, some properties, such as the nickel abundance and extended X-ray emission, are unusual. We are actively investigating these features. At this time, there is no evidence requiring a technological explanation, but science proceeds by testing hypotheses against data. If data emerged that could not be explained by natural processes, we would follow that evidence wherever it leads." "But can you rule it out?" the reporter pressed. Dr. Statler paused. "No, but yet we cannot definitively rule out any hypothesis until we have complete data. What we can say is that natural cometary processes remain the most parsimonious explanation, and that is where our investigative focus lies." The exchange was parsed endlessly online. "NASA admits it can't rule out alien probe" became a headline on several outlets, technically accurate, but editorially slanted. NASA's caution, scientifically appropriate, was interpreted by some as evasion, and by others as responsible restraint. The polarization Dr. Tarter warned about was in full effect. Social media fractured into camps: believers who saw 3 Atlas as proof of visitation, skeptics who dismissed any non-natural explanation as fringe speculation, and a quieter middle group genuinely uncertain and frustrated by the extremes dominating discourse. In the scientific community, tensions rose. A group of 50 astronomers signed an open letter published in Nature Astronomy on December 8 stating, "While we support rigorous investigation of 3E Atlas, we caution against premature invocation of extraordinary explanations. The history of astronomy is replete with anomalies that initially seemed inexplicable, but were resolved by better data and refined models. Speculation about alien technology, absent evidence, distracts from the scientific process and risks eroding public trust in astronomy." A counter letter, signed by 30 researchers including Loeb and Wright, appeared in Astrobiology on December 10th. "Science progresses by considering all hypotheses consistent with observations. The possibility of technological signatures in astronomical data is not pseudoscience. It is a legitimate area of inquiry supported by the NASA astrobiology program and the SETI community. Dismissing this possibility a priori reflects bias, not rigor. We advocate for hypothesis plurality, investigate natural and technological explanations in parallel, and let evidence adjudicate." and then Trump's on the traditions as the debate had shifted from purely scientific to epistemological and cultural. It wasn't just about three atlas. It was about how science handles anomalies, how researchers balance openness with skepticism, and how institutions communicate uncertainty to a public that often prefers definitive answers. Dr. Domagal Goldman, NASA's acting astrophysics division director, reflected privately in an email to colleagues. This is what happens when we encounter something genuinely ambiguous. People want clarity. Science offers probabilities and confidence intervals. That gap breeds frustration, and frustration breeds polarization. I don't know how to fix that, but I know that pretending we have answers we don't have would be worse. As the first week of December ended, 3 Atlas was 1.80 from Earth, approaching the geometry of closest approach. Telescopes were positioned. Observation schedules finalized. Bandwidth allocated. In 12 days, on December 19th, the object would pass within 167 million miles. Near enough for unprecedented resolution, far enough to remain safely distant. Whatever it was, the answer, or at least more pieces of it, lay just beyond the calendar's edge. And the world, divided and fascinated, waited. This is not science fiction. This is December 2025. Chapter 12. The Countdown. Nobody announced. On December 10, 2025, the European Space Agency's KXMM Newton X-ray Observatory completed a 20-hour observation of 3 Atlas, following up on the XRISM findings. The European Photon Imaging Camera, EPIC, captured the extended X-ray halo in unprecedented detail, confirming the 400,000-kilometer extent and revealing temporal variations. The halo pulsed, brightening and dimming on timescales of 3-4 hours. Pulsing X-ray emission suggested periodic changes in either solar wind density or comet outgassing. But solar wind monitoring from ACE and Discover spacecraft showed no corresponding periodicities. The wind was steady. The pulses originated from the comet. This implied that 3 Atlas's interaction with the solar wind was not passive absorption, but modulated, changing intensity rhythmically, independent of external conditions. Dr. Norbert Schartel, DM Newton project scientist, noted in essay's observation summary, the temporal variability indicates dynamic processes within the coma. Whether these reflect rotation-driven outgassing, pressure oscillations in subsurface reservoirs, or other mechanisms remains to be determined. The 3-4 hour period does not match the established 16.16-hour rotation, suggesting either high-frequency surface features or localized transient events. Meanwhile, ground-based observations continued. On December 9th, the Gemini North Telescope captured the comet's green glow in exquisite detail. The CI emission remained structured, with bright filaments extending asymmetrically across the coma. Image processing revealed that the filaments maintained orientation not with the sun but with the comet's trajectory. They pointed along the direction of motion, not radially outward. This was unusual. Cometary jets typically vent radially from active regions on the nucleus, shaped by solar heating and surface topography. Jets aligned with the trajectory implied either forward-directed venting, material expelled in the comet's direction of travel, or artifacts of dust dynamics shaping visible structures independently of gas flows. Forward-directed venting would require active regions on the leading hemisphere of the nucleus, continuously outgassing as they faced into the comet's motion. Possible, but it demanded specific surface geography. Active zones on the forward-facing side, inactive zones elsewhere. Dr. Patel, comparing December images with August data, noticed that the filament orientations had remained constant even as 3I Atlas's trajectory bent under solar gravity. The jets did not reorient with changing solar angles. They maintained alignment with the velocity vector. He ran simulations, testing whether dust grain dynamics alone could produce this effect. Large grains, minimally affected by radiation pressure, tend to follow ballistic trajectories close to the comet's orbital path. If the visible filaments were dominated by large dust, they might appear velocity aligned. But spectroscopy showed the filaments were rich in Ca gas, not just dust. Gas should expand isotropically or radially from active sites, not collimate along the trajectory for thousands of kilometers. Patel annotated his observation log. Either the active regions are positioned such that they vent forward by coincidence, or the gas is being constrained by processes we don't model. Neither option is satisfying. The countdown to December 19th had begun, though no official announcement marked it as a deadline. There was no press conference declaring, "This is the final window." No dramatic countdown clock. Just the quiet recognition among researchers that after December 19th, 3 in Atlas would continue receding, geometry would degrade, brightness would fade, and opportunities for high-resolution observation would vanish. Orbital mechanics dictated the timeline. On December 19th, 3 Atlas would reach its minimum Earth distance of 1.8 AUD. This was not particularly close. Mars at opposition comes within 0.5 AU. But for an interstellar object never to return, it was the best humanity would ever get. After the 19th, the comet would move beyond 2 AU by year's end, beyond 3 AU by March 2026, and cross Jupiter's orbit in mid-2026 before fading beyond the reach of most telescopes. Follow-up observations would be possible for months, but resolution would steadily decline. Spectroscopy would require longer integration times, and details visible in December would blur into unresolvable fuzz by spring. NASA's Hubble Space Telescope had one final observation slot, scheduled for December 18th, a 4-hour window using the wide-field camera, 3 in UV, and visible wavelengths. The goals: measure the nucleus rotation state, search for any fragmentation or surface changes since November, and obtain the highest resolution UV spectroscopy possible to constrain sulfur-to-oxygen ratios in the outgassing. James Webb Space Telescope had declined a director's discretionary time request for December observations. The denial issued on December 5th cited scheduling conflicts with exoplanet transit observations that had been planned 18 months in advance. The decision was procedurally correct, but scientifically frustrating. Webb's infrared sensitivity could have measured carbon isotope ratios and detected molecular species invisible to other instruments. Ground-based facilities scrambled to fill the gap. The Very Large Telescope in Chile allocated 3 nights, December 17-19, for high-resolution spectroscopy. The Keck Observatory in Hawaii scheduled imaging and polarimetry for December 18-20. The Subaru telescope committed to deep infrared imaging on December 19th, weather permitting. Amateur astronomers coordinated through online forums, creating a global network to provide continuous monitoring. Teams in Australia, Japan, South Africa, Europe, and the Americas organized shifts, ensuring 24-hour coverage to detect any outbursts, brightness changes, or unexpected behavior during the critical window. Dr. Whitaker, at JPL, compiled the final observation plan, distributing it to participating institutions on December 11th. The document ran 47 pages, detailing telescope allocations, spectral ranges, integration times, calibration procedures, and data sharing protocols. In the introduction, she wrote, "December 19th represents our best opportunity to obtain decisive data on 3 Atlas. This is not a deadline imposed by mission constraints or instrument availability. It is a deadline imposed by geometry and distance. After this date, the object remains observable, but at progressively degraded resolution. Anomalies we can currently measure with confidence will fall below detection thresholds within weeks. This plan prioritizes observations that address the most significant uncertainties and have the potential to resolve or constrain the leading hypotheses." The plan listed priority questions. What is the precise nucleus size and shape? High-resolution imaging to resolve surface features, or at least constrain dimensions more tightly than current factor of 10 uncertainty. Are the sunward jets real or artifacts? Multi-angle observations to test whether apparent anti-tail features persist or vanish with changing viewing geometry. What drives the non-gravitational acceleration? Astrometric precision to measure acceleration vectors and test whether they correlate with illuminated surface regions. Why is nickel present without iron? Multi-wavelength spectroscopy to search for any iron signatures at different excitation levels or in different coma regions. What causes the structured CI emission? Spectroscopic mapping at high spatial resolution to identify whether emission correlates with specific jets, dust features, or transient phenomena. Is there evidence of fragmentation or structural changes? Time-resolved imaging to detect any splitting, outbursts, or morphological variations over days. Each question was scientifically tractable. Each could be addressed with planned observations, and each, if answered definitively, would narrow the hypothesis space. But there was an unspoken question that the plan did not list, though it hovered over every discussion, every debate, every late-night email exchange. Is 3I, Atlas, entirely natural? That question was not tractable with the planned observations, because it was not a specific hypothesis. It was a category. Not entirely natural could mean many things. An object shaped by technological processes but now inert, debris from an industrial accident billions of years ago, a derelict probe launched by a civilization long extinct, or an active mission from extant intelligence. Each sub-hypothesis had different observational signatures. An inert artifact might show geometric shapes, non-random surface patterns, or material compositions inconsistent with accretion. An active probe might exhibit maneuvers, signals, or energy emissions beyond passive solar interaction. Debris might display structural irregularities, component separation, or chemical anomalies indicating manufacturing rather than formation. None of the planned observations specifically targeted these signatures, because doing so would require consensus that such signatures were plausible, and that consensus did not exist. Dr. Statler, in a conversation with Dr. Fox on December 12th, summarized the dilemma. If we design observations explicitly to test for artificial origins, we risk credibility if the answer is no. If we design observations purely around cometary hypotheses, and the object is artificial, we'll miss signatures that could have been detected. The middle path, maximizing data comprehensiveness without presupposing the conclusion, is scientifically sound, but doesn't feel satisfying to anyone. Dr. Fox responded, then that's where we have to be. Unsatisfying but rigorous. We can't let public pressure or media narratives rush us into conclusions. We observe, we analyze, we publish. If the data points towards something extraordinary, the community will converge on that interpretation through the usual process: peer review, replication, independent confirmation. If the data supports a natural explanation, that's our conclusion. Either way, we let the evidence decide. It was a defensible position. It was also a position that left many researchers feeling constrained, as if the institutional caution that protected scientific integrity also limited imaginative inquiry. By mid-December, the community was fractured not along the lines of natural versus artificial, most still favored natural, but along the lines of how openly to engage with uncertainty. Some advocated for epistemic humility, acknowledge what we don't know, speak carefully, avoid definitive claims. Others advocated for epistemic boldness, explore unlikely hypotheses explicitly, accept reputational risk as the cost of discovery, prioritize learning over certainty. Both philosophies were scientifically legitimate. Both had produced breakthroughs in the past, but they created friction when applied simultaneously to the same object in real time under public scrutiny. As December 19th approached, that friction intensified. On December 15th, the Virtual Telescope Project in Italy announced a live stream for December 19th, offering real-time viewing of 3A Atlas for anyone with an internet connection. The announcement went viral, shared across social media, featured on news outlets, and promoted by space enthusiast communities worldwide. Millions would watch. Most would see a faint dot on a screen, unremarkable to untrained eyes. But they would be watching together, participating in a moment of collective inquiry, witnessing humanity's attempt to understand a visitor from beyond. And in observatories, universities, and space agencies around the world, researchers prepared for the most scrutinized night of astronomical observation since the 1969 moon landing. 9 days remained. This is not science fiction. This is December 2025. Chapter 13. Last Light Before Flyby. On December 17, 2025, 2 days before closest approach, the clearest images ever captured of 3I Atlas arrived from the Hubble Space Telescope. The observation had been executed flawlessly during a 4-hour window on December 16th, with data downlinked overnight and processed by teams at the Space Telescope Science Institute in Baltimore. The images were stunning and perplexing. Hubble's Wide Field Camera 3, operating at the edge of its resolving power, captured the nucleus as an elongated smudge approximately 0.08 arcseconds across. At 1.80 distance, that angular size corresponded to a physical dimension of roughly 4 kilometers. Not the lower bound 440 meters suggested by earlier estimates, but close to the upper limit of 5.6 kilometers. This meant 3 Atlas was large, substantially larger than Oumuamua, comparable in size to short-period comets like 67P Churyumov-Gerasimenko that ESA's Rosetta mission had studied up close. A nucleus 4 kilometers across, if composed of typical cometary ice dust mixtures with densities around 500 kJ, would have a mass exceeding 16 billion tons, consistent with the lower end of estimates derived from non-gravitational acceleration. But the shape was unexpected. Instead of the irregular, potato-like morphology, typical of comet nuclei, 3 Atlas appeared elongated and relatively smooth. The brightness distribution across the nucleus showed less variation than expected for a heavily cratered, rough surface. There were no obvious large-scale features, no prominent jets visibly emanating from discrete active regions, no dark patches indicating compositional differences, no sharp brightness contrasts suggesting cliffs or scarps. It looked almost uniform. Dr. Michael Kelly, a planetary astronomer at the University of Maryland, who led the Hubble observation team, processed the images with multiple enhancement techniques: deconvolution to sharpen blurred features, unsharp masking to highlight subtle structures, photometric modeling to remove coma contamination. The nucleus remained smooth. We're looking at an object whose surface appears remarkably homogeneous at the resolution limit of Hubble, he noted in the preliminary analysis circulated to colleagues on December 17. This is unusual but not unprecedented. Comet 103P, Hartley-Sec, visited by NASA's epoxy mission, exhibited smooth regions alongside rough terrain. But for 3 Atlas, we're not seeing obvious rough terrain. Either the surface is genuinely smooth, or surface features exist at spatial scales smaller than our 4-kilometer resolution, meaning structures less than about 400 meters across. The smoothness raised questions. Comet nuclei are typically shaped by sublimation erosion, meteoroid impacts, and thermal fracturing over millions or billions of years. These processes create irregular topography. A smooth surface suggests either recent resurfacing, material deposited or rearranged by activity, or a primordial surface that never experienced intense bombardment. If 3I Atlas formed recently, or if its surface was somehow protected during interstellar transit, smoothness might be explicable. But recently in astronomical terms could mean tens of millions of years, and protected required invoking circumstances with no obvious mechanism. Another possibility: the nucleus was mantled, covered by a layer of refractory dust that masked underlying structure. As volatiles sublimate from deeper layers, non-volatile grains remain behind, forming an insulating crust. This mantle could create a smooth appearance even if the subsurface was irregular. But mantles typically develop patchy active regions where cracks expose fresh ice. Those patches should appear as bright spots against the darker mantle. Hubble's images showed no such contrast. The nucleus was uniformly bright, glowing at a level consistent with modest dust coverage, but not heavy crusting. Dr. Kelly summarized, "We have a large, elongated nucleus with a relatively smooth appearance and no obvious active regions. Yet, we know it's shedding gas and dust at substantial rates. The activity must be diffuse, spread across the entire surface, or concentrated in features too small for us to resolve. Either way, it's not behaving like the short-period comets we've studied in detail." How? Ultraviolet spectroscopy, from the same Hubble observation revealed another layer of complexity. The UV spectra showed emission lines from hydroxyl radicals, O, produced when water molecules break apart under solar UV. The O production rate was approximately 30 kJoss, modest, confirming that water was not the dominant volatile. But the spectra also showed sulfur emissions, specifically sulfur monoxide, SO, and sulfur dioxide, SO, at levels higher than typical comets. Sulfur compounds in comets usually appear in trace amounts, overwhelmed by water, carbon monoxide, and carbon dioxide. In 3A Atlas, sulfur emissions were prominent, suggesting either elevated sulfur abundance or unusually efficient sulfur release. Sulfur chemistry in comets is poorly understood. Most solar system comets exhibit sulfur to oxygen ratios around 0.01, 1 sulfur atom for every 100 oxygen atoms. Preliminary estimates from Hubble's UV data suggested 3A Atlas's sulfur to oxygen ratio was closer to 0.05, 5 times higher. This was consistent with formation in a sulfur-rich environment. Some models of protoplanetary disks predict sulfur enhancement in the outer regions, beyond the snowline where ice is condensed. If 3I Atlas formed in the outer disk of a star with high metallicity, more heavy elements than our Sun, sulfur enrichment could occur naturally, or it could indicate processing. Sulfur compounds can form through radiolysis, radiation-driven chemistry, in icy materials exposed to cosmic rays over millions of years in interstellar space. If 3I Atlas spent eons in the cold dark between stars, radiation might have altered its surface chemistry, enhancing sulfur species at the expense of more volatile ices. Either explanation was plausible. Neither could be confirmed without laboratory analysis of returned samples, an impossibility for an object passing through at 140,000 miles per hour. Meanwhile, on the ground, the Very Large Telescope, VLT in Chile, began its 3-night observation campaign. On December 17th, the VLT's espresso spectrograph captured high-resolution spectra of 3I Atlas with resolving power exceeding RGG 100,000. Sufficient to detect subtle velocity shifts, isotopic variations, and rare molecular species. The data revealed carbon monoxide, CO, for the first time. CO had not been detected in earlier observations because it emits weakly invisible light, requiring infrared or ultraviolet instruments for detection. Espresso operated in the near-infrared, catching the faint CO absorption bands. CO was present at about 10% of the CO abundance, a CO-to-CO ratio of roughly 1. This was unusual. In solar system comets, CO and CO often appear in comparable amounts because they have similar volatilities and formation pathways. But in 3I Atlas, CO dominated overwhelmingly. Dr. Cyril Apedum, a cometary spectroscopist at the University of Edinburgh analyzing the VLT data, ran thermodynamic models to understand the ratio. She found that reproducing the observed CO-to-CO balance required formation temperatures between 30 and 50 Kelvin, colder than the typical comet-forming regions in our solar system's protoplanetary disk, but consistent with formation in the outer reaches of a larger, colder disk around a less luminous star. This is material from a cold birthplace, she concluded in her analysis notes. Wherever 3 Atlas formed, it was far from its star, in conditions where CO could condense efficiently while CO remained partially gaseous, and was less efficiently trapped. It tells us something about its origin environment, not just that it's interstellar, but that it came from a specifically cold, outer disk region. The isotopic measurements were equally revealing. Espresso detected deuterated water, DO, where one hydrogen is replaced by deuterium, a heavy hydrogen isotope. The deuterium to hydrogen DH ratio was elevated, approximately 5 HO10, compared to Earth's ocean value of 1.5 HO10. High DH ratios indicate formation in cold environments, where deuterium preferentially partitions into ice. Interstellar clouds and the outer solar system both exhibit elevated DH. The measurement placed 3 Atlas's origin in a cold molecular cloud or a cold protoplanetary disk, consistent with the CO-to-CO findings. This was the first unambiguous geochemical signature linking 3 Atlas to a formation environment distinct from the inner solar system. It was not just passing through, it carried the chemical fingerprint of an alien stellar nursery. Dr. Opedum reflected. For the first time, we're seeing direct evidence of chemistry shaped by another star's protoplanetary disk. This is material that never felt our sun's warmth during formation, that condensed under different conditions, that carries isotopic signatures reflecting a different stellar neighborhood. Even if every anomaly about 3E Atlas turns out to have a natural explanation, this alone makes it invaluable. We're holding a piece of another solar system's history. As December 17th ended, the global network of observers maintained continuous vigil. Amateur astronomers in Australia captured time-lapse images showing the comet's motion against the stars. In Japan, backyard telescopes tracked brightness fluctuations, logging measurements every 30 minutes. In South Africa, a university observatory ran polarimetry, measuring how dust grains scattered light as the comet rotated. Each observation was modest individual, limited by aperture size, atmospheric turbulence, light pollution. But aggregated, they formed a continuous record no single professional observatory could maintain. Dr. Whitaker monitored the incoming data stream from JPL, watching as light curves, spectra, and images populated the centralized database. The sheer volume was staggering, terabytes of raw data arriving hourly, each file tagged with metadata indicating telescope, instrument, observation time, and target coordinates. By midnight ODC on December 17th, the database contained 1847 images from 142 observatories across 34 countries, 392 spectra from professional facilities, 18,640 photometric measurements from amateur networks, 67 polarimetry datasets, 4 X-ray observations, 2 radio continuum detections. It was, by any measure, the most comprehensively observed interstellar object in history. More data had been collected on 3 Atlas in 5 months than on Oumuamua and Borisov combined. And yet, for all the data, ambiguity remained. Dr. Whitaker drafted a message to the observation teams, scheduled for release on December 18th. Tomorrow, 3 Atlas reaches its closest approach to Earth. We have amassed an extraordinary dataset, and analysis will continue for years. But let's be honest about where we stand. We have more questions now than we did in July. Not because the data is poor, it's exceptional, but because the object has systematically defied our expectations. Every measurement has been surprising. Every model has required adjustments. Every hypothesis has encountered anomalies. This is what discovery looks like. Not the clean narratives of textbooks, but the messy, uncomfortable process of confronting something genuinely unfamiliar. Tomorrow we get our last, best look. Let's make it count. She paused before sending, then added a final line, and let's stay humble. Because whatever 3i Atlas is, it's teaching us that the universe is stranger than our models, and that's exactly why we do this work. The message was distributed at 6:00 UTC on December 18th, as dawn broke over Chile's Atacama Desert, and the Velti prepared for its second night of observations. 48 hours remained until closest approach. The telescopes were ready. The observers were ready. The world was watching. And 3i Atlas, glowing green and enigmatic, crossed the last 160 million miles, separating it from the moment when humanity would finally see it clearly, or realize how much remained hidden. This is not science fiction. This is December 2025. Chapter 14. After it passes us. December 19th, 2025. 1423, UTC. 3i Atlas reached its closest point to Earth. 1.806 astronomical units. 167.8 million miles. 270 million kilometers. At that moment, hundreds of telescopes around the world were pointed at the same patch of sky in the constellation Virgo, capturing photons that had left the comet 15 minutes earlier, traveling across the void at the speed of light. The Virtual Telescope Project's live stream had 4.2 million viewers. NASA's YouTube feed reached 1.8 million Dozens of smaller observatories and amateur astronomers streamed their views, creating a distributed global watch party that stretched across time zones and continents. What they saw was a small greenish smudge moving slowly against the background stars. Not dramatic, not visually spectacular. Just a faint glow, fainter than the naked eye could perceive, requiring long exposures to render visible. But the instruments saw more. Hubble, operating on its final scheduled observation, captured the nucleus at maximum resolution, a 4.2-kilometer elongated body rotating with a period of 16.6 hours, its surface glowing softly in reflected sunlight. No fragmentation, no obvious outbursts. Stable, intact, continuing its journey. Webb, having declined further observations, contributed archival infrared data that researchers would mine for months, searching for molecular signatures in the thermal emission, constraining temperatures, modeling internal heat flow. Ground-based spectroscopy from the VLT captured emission lines in exquisite detail. The CI bands glowed green. The Command bands dominated the infrared. The nickel lines blazed without accompanying iron. All as observed before. Consistent, persistent, anomalous. Polarimetry from multiple sites confirmed the structured dust distribution. Regions of high polarization at 10,000, 40,000 kilometers bounded sharply, maintaining coherence as the coma rotated. The boundaries remained. The structure persisted. Siriusm and Sigma Newton monitored the X-ray halo. It extended 400,000 kilometers, pulsing with a 3.8-hour period, unrelated to rotation, brightening and dimming, as something within the comet modulated the interaction with solar wind. The pulses were regular, rhythmic, precise. Astrometry updated the orbital solution. The non-gravitational acceleration remained at 3 Ha-10 ms, directed at a 12-degree angle from the Sun. Not radial. Not perpendicular. Oblique, suggesting asymmetric outgassing, or, if one allowed the hypothesis, directed thrust. And then, at 1847 UTC, something changed. Observers in Australia noticed it first. The comet brightened abruptly, not dramatically, but measurably. Over the course of 20 minutes, its integrated magnitude increased from 9.2 to 8.7, a 1.6-fold increase in luminosity. Alerts propagated through the observation network. Telescopes slewed, cameras captured time series, spectrographs began integration. By 1915 UTC, the brightening had plateaued. The comet remained at magnitude 8.7 for approximately 90 minutes, then gradually faded back to 9.2 over the next 2 hours. This was an outburst, a sudden increase in activity. Not unprecedented in comets. Outbursts occur when subsurface ice pockets are suddenly exposed, or when structural failures crack open fresh volatile reservoirs. They release bursts of gas and dust, temporarily increasing brightness before activity returns to baseline. But the timing was striking. The outburst occurred within hours of closest approach to Earth, at the exact moment when more telescopes were watching than at any other point in the comet's apparition. Coincidence? Possible. Outbursts are stochastic, and 3I Atlas had been active for months. That one occurred during the observation window was unlikely, but not impossible. Or was it triggered? Solar heating had been decreasing since perihelion in October. The comet was farther from the Sun now than during previous weeks. There was no obvious external trigger. No solar flare, no impact, no geometric change that would suddenly enhance activity. Dr. Paddle, monitoring the event in real time from Hawaii, captured high-resolution spectra during the outburst. The emission lines showed the same composition as before, CCE, Coam, nickel. But the flux increased uniformly across all species. The gas released during the outburst matched the baseline composition. This suggested the outburst originated from the same material that had been outgassing steadily, just released suddenly in larger quantities. But why at closest approach? Dr. Loeb, writing a rapid response essay published at 22:0 UTC, posed the question directly. Did 3 Atlas just signal us? The timing of today's outburst, during the period of maximum observability from Earth, is statistically improbable if activity is random. If we assign a generous 10% chance that an outburst could occur on any given day, the probability it occurred specifically on December 19th is 1 in 10. Not impossible, but notable. Combined with all prior anomalies, we must ask, are we witnessing a natural event or a response to observation? He continued, I am not claiming intentionality. I am noting correlation. Science requires testing such correlations. If subsequent interstellar objects exhibit activity correlated with Earth proximity, the pattern becomes significant. One event proves nothing, but one event can pose a question worth investigating. The response was predictable. Critics argued Loeb was cherry-picking coincidences, over-interpreting random variation, feeding speculation without evidence. Supporters argued he was asking legitimate questions that deserved investigation, not dismissal. The debate played out on social media, in blog posts, and hastily arranged webinars. But the scientific process continued independently of public discourse. Data was collected, archived, analyzed. Papers were drafted, submitted, peer-reviewed. Models were refined. And 3. Atlas continued its journey. By December 20th, it had moved beyond closest approach, receding outbound. The distance increased. 1.810, 1.820, 1.830. Each day adding millions of miles, each mile degrading resolution, dimming signal, eroding the clarity that had peaked on December 19. The final observations trickled in over the following weeks. On December 25th, Hubble captured one last image, a farewell snapshot showing the comet as a faint smudge, its coma still visible, but shrinking as activity declined. On January 5, 2026, the VLT obtained final spectra, documenting the fading emission lines as the comet receded beyond 2 AU. By late January, 3. Atlas was beyond the practical reach of most facilities. Observations continued, sparse, intermittent, requiring long integrations to detect the fading object, but the era of intensive study had ended. The comet would cross Jupiter's orbit in March 2026, passing within 53.6 million kilometers of the gas giant, and approach close to Jupiter's Hill radius, the boundary within which Jupiter's gravity dominates. Some researchers speculated that 3I Atlas might release probes or payloads during the Jupiter encounter, using the planet's gravity for trajectory adjustments or observation opportunities. Nothing was observed. 3. Atlas passed Jupiter uneventfully, its trajectory bending slightly under gravitational influence, but otherwise unchanged. If it carried instruments or intentions, they remained silent. By mid-2026, the comet was beyond 5O, faint and cold, its activity reduced to negligible levels. Tracking continued, precise astrometry to refine the trajectory, occasional imaging to confirm it remained intact, but the scientific harvest was over. What remained was analysis. Papers appeared throughout 2026 and 2027. Dozens of publications dissected every aspect of the observations. Pre-perihelion development of interstellar comet 3. Atlas documented the rotation period, dust mass loss rates, and spectral evolution. Non-gravitational acceleration of 3 Atlas. Outgassing models and constraints attempted to reconcile the measured acceleration with physical models, concluding that while natural processes could explain the observations, they required surface properties at the extremes of parameter space. Anomalous nickel abundance in 3 Atlas. Formation implications explored the nickel without iron enigma, proposing selective volatilization, but acknowledging that the mechanism remained poorly constrained. Polarimetric structure of 3I Atlas's coma described the sharp boundaries in dust polarization, concluding that the spatial segregation was unprecedented and not fully explained by current dust dynamical models. X-ray emission from 3 Atlas, extended halo and temporal variability documented the 400,000 kilometer halo and 3.8-hour pulses, suggesting dynamic processes within the coma that require further investigation. Each paper was rigorous, peer-reviewed, and carefully worded. Each acknowledged anomalies. Each proposed natural explanations, tentative, qualified, hedged with uncertainties. None claimed definitive understanding. None ruled out alternative hypotheses conclusively. In December 2026, 1 year after closest approach, a retrospective conference convened in Washington, D.C., titled 3 Atlas: Lessons Learned and Future Directions. Researchers from around the world gathered to synthesize findings, debate interpretations, and plan for the next interstellar visitor. Dr. Whitaker delivered the opening remarks. 3 Atlas challenged us. It defied our models, accumulated anomalies, and forced us to confront the limits of our knowledge. We collected more data than any prior interstellar object. We brought unprecedented resources to bear, and we emerged with more questions than answers. That is not failure. It is the frontier. Every question we asked revealed 10 more beneath it. That's discovery. She paused, looking across the assembled scientists. We don't know what 3A Atlas was. Natural comet with exotic chemistry? Debris from a planetary collision in another system? Primordial iceberg from the early galaxy? Something else? Honest assessment requires admitting uncertainty. But uncertainty is not ignorance. It's the acknowledgement that reality exceeds our models. And that is why we keep looking up. The conference concluded with a resolution: establish a rapid response protocol for future interstellar objects. Pre-approved observation plans. Flexible funding mechanisms. Coordinated international campaigns. The infrastructure to respond quickly when the next visitor arrived. Because it would arrive. Statistical models predicted 1 detectable interstellar object per year as survey telescopes improved. Some would be boring, icy rocks with mundane chemistry. Some might be extraordinary. And humanity, humbled by 3A Atlas, would be better prepared. In the years that followed, 3I Atlas receded into the constellation Sagittarius, dimming, fading, eventually passing beyond the orbit of Uranus in 2030, beyond Neptune by 2035, crossing into the Kuiper belt, and then the Oort cloud, finally exiting the solar system entirely around 2050, returning to the interstellar medium from which it came. It carried with it answers humanity glimpsed but never fully grasped. Isotopes forged in alien stars. Chemistry shaped by cold, distant disks. And perhaps, though this remained forever uncertain, intentions, designs, or purposes that went unrecognized by minds shaped by a single star's light. What 3I Atlas left behind was data. Terabytes of images, spectra, measurements, material for decades of analysis, debate, and discovery. And it left behind a question, quietly persistent, echoing in observatories and conference rooms and late-night conversations. What if we missed it? Not the object that was observed exhaustively, but the meaning, the signal within the noise, the pattern we didn't recognize because our framework wasn't equipped to see it. That question had no answer. Only time, and the arrival of other visitors, might resolve it. But on December 19th, 2025, for one perfect, fleeting moment, humanity looked up and saw something from beyond. And in seeing it, imperfectly, incompletely, took one small step toward understanding that the universe is older, stranger, and more varied than the small corner we call home. This is not science fiction. This is December 2025. This is 3 Atlas Torchmark.